Right now, you're a passenger on a colossal spaceship. A world teeming with life, hurtling through the silent void of space at a speed that would shatter the sound barrier. You're traveling at roughly 1,040 miles per hour, or for our metric friends, about 1,670 kilometers per hour. And yet, you can't feel a thing. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. You can sip your coffee without it sloshing. You can stand perfectly still without a whisper of wind. It's the most extreme ride you'll ever take, and you're on it for life, yet it feels as calm as solid ground. Because it is solid ground. It's the Earth. We almost never think about it, but this silent, relentless rotation is the master puppeteer of our world. It secretly pulls the strings of your life in ways you might not expect. It dictates when you wake and sleep. It commands the winds, stirs the oceans, and draws the map for our weather. It even subtly changes your weight. This spin isn't just a fun piece of cosmic trivia. It's the architect of our biology, the engine of our climate, and the silent clockwork that governs our civilization. But how? How does this imperceptible motion, this grand planetary waltz, have such a profound and intimate impact on our daily lives? Today, we're exploring the physics you can't feel. We're going to uncover the hidden forces born from this spin and reveal how the simple fact that our world turns is responsible for nearly everything you experience. From the storm brewing outside, to the jet lag from a long flight, to the very reason you get tired at night. It all comes back to this one, silent motion. You're hurtling through space at over 1,000 miles per hour right now, but you can't feel a thing. This invisible spin dictates everything from your sleep schedule to the weather, and we're going to explain how. So, how does this imperceptible motion have such a profound impact? To understand that, we first have to understand why we don't feel it. The reason is surprisingly simple: consistency. The Earth spins at a virtually constant speed. And crucially, everything attached to it, the oceans, the atmosphere, and you, is spinning right along with it. Think of it like being in an airplane cruising at a steady 500 miles per hour. As long as the plane isn't speeding up, slowing down, or hitting turbulence, you can walk down the aisle and feel perfectly normal. Your body is moving at the same speed as the plane, so relative to the plane, you're not moving at all. Now, just apply that to the entire planet. We are all passengers on a perfectly smooth ride. There's no sudden acceleration to push you back in your seat or sudden stop to throw you forward. We are in a state of equilibrium. Gravity, the force pulling us toward the center of the planet, is immensely more powerful than the gentle outward push from the spin, known as centrifugal force. In fact, at the equator where the spin is fastest, the centrifugal force is only about 0.3% of gravity's pull. That's why you don't just fly off into space. Gravity has you firmly anchored. But just because you can't feel it doesn't mean its effects aren't everywhere. And the most obvious, most profound effect is the one that governs the very rhythm of our existence. The master clock, day, night, and your internal rhythm. Every single day of your life is defined by one simple event. The sun appears to rise, travel across the sky, and set. This isn't because the sun is moving, of course, but because you are. Our planet's eastward rotation carries us into the sunlight and then back out into the darkness, over and over. This cycle is the most fundamental metronome of life on Earth. This daily pattern of light and dark has been one of the single greatest influences on the evolution of life. It's not just in our behavior, it's written into our very biology, into the deepest machinery of our cells. We call this the circadian rhythm. Coming from the Latin, circadium, meaning around a day, it's your internal, biological clock that ticks in a roughly 24-hour cycle, governing thousands of processes in your body. This isn't just a preference for being awake during the day. It's a deeply ingrained, genetically programmed system. In your brain, a tiny region called the suprachiasmatic nucleus, or SCN, acts as the master clock. It's made of about 20,000 nerve cells and sits just above where your optic nerves cross, giving it a direct line to your eyes. When light enters your eyes in the morning, it sends a powerful signal to the SCN that says, "The day has begun." The master clock then sends out a cascade of messages. It tells your adrenal glands to ramp up cortisol, which acts as a natural stimulant, raising your blood sugar and heart rate to get your body ready for the day. As the day goes on, your circadian rhythm influences your metabolism, digestion, immune function, and even your mood. Then, as darkness falls, your eyes report the absence of light. The master clock takes this cue and instructs the pineal gland to start producing melatonin, the herald of the night. Melatonin signals that it's time to wind down. Your body temperature drops, your metabolism slows, and you begin to feel sleepy. This intricate dance of hormones, all synchronized by the sun, is a direct consequence of Earth's rotation. Imagine a world that didn't rotate. One half would be locked in perpetual, scorching daylight, while the other would be frozen in endless night. The very concept of a day wouldn't exist, and neither would the internal clock that tells you when to rest. The power of this clock is so profound that we feel its disruption intensely. This is what we call jet lag. When you fly across several time zones, your internal clock is still synced to your home location. If you fly from New York to Paris, your body thinks it's still evening when the Parisians are waking up. Your brain is still screaming for melatonin, but the local environment is telling you to be awake. The result is a miserable period of fatigue and disorientation as your master clock painstakingly resets itself to the new cycle of light and dark. It's a visceral reminder that you have a planetary rhythm built into your very being. This 24-hour cycle also created our global system of timekeeping. Time zones are a human invention designed to standardize our clocks with the sun. There are 24 standard time zones, each creating a world where the clock time generally matches the time of day. Every international phone call, financial transaction, and flight schedule is coordinated around this system, a system that exists only because our planet turns. So, the next time you feel that wave of sleepiness at night, remember what's really happening. You're feeling the pull of 1 billion years of evolution, a biological legacy gifted to you by the silent, steady spin of our world. The hidden hand, Coriolis, weather, and oceans. While day and night are the most obvious results of Earth's spin, there's a much more subtle, phantom-like force at play. It's an effect you can't see or feel, but it shapes our world on a colossal scale. It dictates the direction hurricanes spin, steers massive ocean currents that regulate our planet's temperature, and charts the course of the very air we breathe. This invisible hand is called the Coriolis effect. To get it, picture yourself on a giant, spinning merry-go-round with a friend in the center. If your friend tries to throw a ball directly to you on the outer edge, what happens? From their perspective, they threw it in a straight line. But because the ride is spinning, you've moved by the time the ball reaches the edge. From your point of view, the ball appears to curve away. That apparent deflection is the Coriolis effect. It isn't a true force like gravity. It's an asterisk apparent force that arises because we're observing from a rotating frame of reference. The Earth is that giant merry-go-round. Now, let's scale this up. The Earth spins fastest at the equator, about 1,670 kilometers per hour, 1,040 miles per hour. Near the North Pole, however, a person is barely moving, mostly just spinning in a small circle. This difference in speed is the key. Imagine a pocket of warm air near the equator, moving north. As it travels, it moves over ground that is spinning more slowly. But the air retains its initial high-speed eastward momentum. The result? Relative to the slower-moving ground, the air gets deflected to the east, or to its right in the northern hemisphere. This is the golden rule. In the northern hemisphere, moving objects are deflected to the right, and in the southern hemisphere, they're deflected to the left. This simple rule is the architect of our planet's entire circulatory system. Without rotation, wind would just flow from the hot equator to the cold poles and back again. But the Coriolis effect shatters this simple model, breaking the atmosphere into a complex series of rotating cells that create our dominant wind patterns, like the trade winds and the westerlies. These winds were the highways for the age of sail and still influence our weather daily. The most dramatic demonstration of this is a hurricane. These storms are giant engines feeding on warm ocean air. As warm, humid air rises, it creates a low-pressure area, and surrounding air rushes in. On a non-rotating planet, it would rush straight to the center. But on our spinning Earth, the Coriolis effect takes hold. In the northern hemisphere, the incoming air is deflected to the right, forcing it to spiral inwards and creating the storm's characteristic counterclockwise spin. In the southern hemisphere, the deflection is to the left, so cyclones spin clockwise. This is also why hurricanes can't form right at the equator. The Coriolis effect is zero there, so there's no force to start the spin. The same principle governs our ocean currents. Wind blowing on the water gets it moving, and the Coriolis effect deflects it, creating massive circular currents called gyres. In the North Atlantic, this creates the Gulf Stream, a powerful current of warm water flowing from the Gulf of Mexico toward Europe. This single current has a monumental impact on the climate, transporting heat that keeps Western Europe significantly warmer than it would otherwise be. London, for example, is at the same latitude as Calgary, Canada, but its winters are far milder thanks to the Gulf Stream. So when you see a satellite image of a perfectly spiraled hurricane, you're witnessing the work of Earth's rotation. The silent spin of our world is the hidden choreographer of our atmosphere and oceans. The surprising consequences. The effects of Earth's spin go far beyond sleep and weather. It has shaped the very planet we stand on, it subtly alters the physics of our daily lives, and it's even being changed, ever so slightly, by us. First, the shape of the Earth. We're taught it's a sphere, but it's more of an oblate spheroid. It bulges at the equator and is slightly flattened at the poles. The reason? That same centrifugal force. The constant spin creates an outward push, and over billions of years, this has caused the planet to widen at its middle. The Earth's diameter at the equator is about 43 kilometers, or 27 miles, wider than from pole to pole. This bulge means you actually weigh about 0.5% less at the equator than you would at the North Pole, because you're farther from the Earth's center of mass and the outward spin counteracts a tiny fraction of gravity. This same physics affects modern travel. You may have heard that flights going east are faster because of the Earth's rotation, but that's not quite the whole story. The main reason is that Earth's rotation creates powerful high-altitude winds called jet streams, which blow from west to east. Flying east means catching a massive tailwind that can be over 100 miles per hour, while flying west means fighting it. The rotation itself gives a tiny extra boost, but the jet stream does most of the work. For rocket launches, however, that rotational boost is critical. Launching a rocket eastward from near the equator gives it a free speed boost of over 1,600 kilometers per hour, saving enormous amounts of fuel. But perhaps the most astonishing consequence is that the Earth's rotation isn't constant. The length of our day is slowly getting longer, mainly because of the Moon. The Moon's gravity creates ocean tides, and as the Earth turns, the friction of those tides dragging across the ocean floor acts like a brake, slowing us down. It's happening at an average of about 1.8 to 2.3 milliseconds per century. During the age of the dinosaurs, a day was only about 23 hours long. To account for this drift, timekeepers have occasionally added a leap second to our clocks. But these have been a nightmare for modern computer systems, so an international body voted to abolish the leap second by 2035. Recently, however, things have gotten weird. Since 2020, the long-term slowing trend has been temporarily overtaken by a mysterious speed-up, causing some of the shortest days ever recorded. This is likely due to shifts in the Earth's liquid core. At the same time, another powerful force has entered the equation: us. Climate change is melting polar ice, redistributing trillions of tons of water from the poles toward the equator. Just like a spinning ice skater who slows down by extending her arms, moving mass away from the poles is putting a brake on the planet. This human-caused slowing is so significant that it has postponed the potential need for the first ever negative leap second, a second removed from the clock to account for the core speed up. Scientists had predicted this might be needed around 2026, but the braking effect from melting ice has pushed that possibility back to at least 2029. Even our engineering projects have a measurable impact. The construction of the massive Three Gorges Dam in China shifted enough mass to increase the length of the day by an estimated 0.06 microseconds. We are no longer just passengers, we are a geological force, tweaking the fundamental clockwork of our world. From the moment you're born, your life is lived to the rhythm of a silent, planetary dance. It's a spin so constant you can't feel it, yet so powerful it carves the path of hurricanes and orchestrates the symphony of sleep inside your cells. It's a force that has sculpted our world, given us our days and nights, and powered the great ocean currents that regulate our climate. The rotation of the Earth isn't just a science fact. It's in the jet stream that shortens your flight. It's in the swirl of a storm. It's in the very beat of your own internal clock. And now, we've entered an era where our collective actions, melting ancient ice and building colossal structures, are feeding back into this planetary system. We are subtly, but measurably, changing the very spin of our world. It's a humbling realization of our own impact. So the next time you wake up to the morning light, check the weather, or feel the weary pull of jet lag, take a moment. Remember the silent, powerful spin that governs it all. Remember that you are standing on a magnificent, dynamic machine, and its constant, graceful rotation is the secret engine that drives your life. What other invisible forces do you think are shaping our world? Let us know your thoughts in the comments below. And if you enjoyed this journey into the hidden physics of our planet, be sure to subscribe so you don't miss our next exploration into the wonders of our universe. Your body has a 4 billion-year-old clock. There is a rhythm that runs through you, a clock ticking away inside your cells. It quietly shapes your energy, your hunger, and your sleep. But this clock was not built by human hands. It was assembled over billions of years, synchronized to the turning of the Earth itself. This is the story of that clock, of the one cosmic cycle you can never truly escape, and how it connects you to the earliest moments of life on this planet. This is not just a story about time. It is a story about the fundamental workings of your own body. It explains the subtle, predictable shifts you feel every day. The alertness that arrives in the morning, the heavy-lidded feeling that washes over you in the afternoon, and the way sleep can feel immediate one night and impossible the next. The answers are not in our daily schedules or our ambitions. They are written in our biology, a legacy passed down from the first life that ever anticipated a sunrise. To understand this clock is to understand something essential about ourselves. We are creatures of rhythm, our bodies shaped by the Earth's daily dance with the sun. And in our modern world, we have created a fundamental conflict with this ancient programming. The light from our screens, the caffeine in our cups, the schedules we keep, they all push against a directive that is billions of years old. This is the story of that conflict, and how learning to listen to your ancient, internal clock is one of the most important things you can do for your health and your connection to the world around you. The daily rhythm. It's worth considering the rhythm of your day. Not the one dictated by alarms and meetings, but the one playing out quietly inside your own body. It is a silent, invisible process, and it performs the same sequence every single day, whether you are paying attention or not. It begins before you open your eyes. In the final hours of sleep, as darkness begins to fade from the outside world, your body is already preparing for the day. A hormonal signal, a wave of cortisol, starts to wash through your system. This is not the chronic, stressful kind of cortisol we often hear about. This is a natural, get up and go signal. It is a biological prompt, designed to gently pull you from sleep, raise your body temperature, and prime your muscles and mind for action. When an alarm finally sounds, your body has already been preparing for an hour, warming its engine. This is why that first hour or two after waking can be a period of such mental clarity. Cortisol is high, the brain is alert, and you are ready for demanding tasks. Blood pressure rises, heart rate quickens, and metabolism kicks into a higher gear. Evolutionarily, this was the time to hunt, to gather, to make critical decisions. Your body still carries a memory of this. By mid-morning, around 10 a.m., you are likely at your peak of alertness. Short-term memory is sharp, focus is intense, and the ability to analyze information is at its zenith. Your body is a finely tuned machine, running a program optimized over countless generations for performance in the morning light. But then, it happens. The afternoon slump. Sometime after lunch, usually between 1 p.m. and 3 p.m., a wave of lethargy can set in. Focus blurs, eyelids feel heavy, and the desire for rest can become overwhelming. This is not a personal failing or a lack of willpower. It is a programmed and predictable part of the daily rhythm. Your core body temperature, which had been rising all morning, takes a slight but significant dip. This dip mimics the temperature drop that helps initiate sleep at night, triggering a powerful signal for rest. At the same time, the stimulating effects of morning cortisol are wearing off. This is a biological siesta, a remnant of a time when our ancestors in warmer climates would have sought shelter from the intense midday sun. It is not a sign of laziness, it is a sign that an ancient clock is still ticking. As afternoon progresses into evening, another profound shift occurs. When the sun dips lower in the sky, the quality of light changes, becoming warmer and redder. Your eyes perceive this and send a critical message to your brain: the day is ending. In response, your body begins to suppress cortisol and starts a new process, the release of melatonin. Often called the hormone of darkness, melatonin is what guides you towards sleep, and its release is deeply sensitive to light. It signals to every cell in your body that it is time to wind down. Your blood pressure and core body temperature begin their slow, steady decline. Your digestive system slows, preparing for its nightly fast. Your brain activity shifts, moving away from alert, analytical thought and toward a more relaxed state. This intricate dance is why you feel hungry at certain times, why you might have more energy for a workout in the late afternoon, and why your body temperature is lowest in the pre-dawn hours. It is a 24-hour operating system governing nearly every aspect of your existence. Not just a sleep-wake cycle, but a master program for metabolism, immunity, mood, and even cellular repair. This daily schedule is known as your circadian rhythm, from the Latin, circadium, meaning, about a day. And what is most remarkable about it is not just that it exists, but where it comes from. This is not a program that was written in your lifetime. It was written at the dawn of life itself. The master clock. So, how does this precise internal schedule actually work? The answer lies deep within the brain, in a structure called the suprachiasmatic nucleus, or SCN. Composed of just 20,000 neurons, the SCN sits in the hypothalamus, positioned strategically right above the point where your optic nerves cross. Think of the SCN as the conductor of a vast orchestra. Every organ, every tissue, every cell in your body is a musician with its own internal clock. Your liver has a clock that dictates the timing of metabolic processes. Your pancreas has one that controls insulin secretion. But without a conductor, this orchestra of trillions would quickly descend into chaos. The SCN is the conductor that ensures every player is in sync, playing in harmony. But how does the conductor know when to start? Its location is key. Sitting just behind the eyes, the SCN receives direct information about the most important time-giving cue on our planet: light. When light, particularly the blue spectrum light of morning, enters your eyes, it travels along a special neural pathway straight to the SCN. This light signal is the daily reset button for your master clock. This daily synchronization is critical because of a fascinating quirk in our biology. Our internal clock does not run on a perfect 24-hour cycle. Left in a dark cave with no external cues, the average human body clock will drift, running on a cycle that is often slightly longer than 24 hours. This means that every single day, your brain has to make a slight adjustment to stay locked in with the Earth's rotation. Morning light is the tool it uses to make that correction. It is the anchor that prevents your internal time from drifting away. The actual timekeeping mechanism within each cell is a marvel of molecular biology, a discovery so profound it earned a Nobel Prize in 2017. At its heart is an elegant genetic feedback loop. Throughout the day, specific genes, like clock and BMAL1, act as activators. They turn on other genes, namely period, per, and cryptochrome, cry. As the day progresses, the proteins produced by these genes, per and cry, slowly build up. As evening approaches, they accumulate to a critical level and move into the cell's nucleus. Once inside, they act as repressors, switching off the very genes that created them. It is a beautiful negative feedback loop. Throughout the night, with the activator genes silenced, the per and cry proteins slowly degrade. By morning, their levels are so low that they no longer block the activators. The genes switch back on, and the entire cycle begins anew. This rhythmic turning on and off of genes is the ticking of your biological clock. The SCN, reset by morning light, then uses nerve signals and hormones to broadcast the correct time to the rest of the body. It tells the pancreas when to prepare for food, the gut when to digest, and the pineal gland when to release melatonin to prepare for sleep. This hierarchical system ensures that your entire physiology is a coordinated machine, aligned with the endless cycle of day and night. It is a system of breathtaking elegance, and its origin story is the story of life itself. The origin story. To find the first tick of this clock, we have to travel back billions of years. Imagine the early Earth. It was spinning much faster than it does today, a legacy of the cosmic collisions that formed it. A day may have been far shorter than our current 24 hours. The Moon, much closer than it is now, exerted a powerful gravitational force, acting like a brake on our planet, gradually slowing its rotation. It was into this world of predictable cycles of light and darkness that life first emerged. Around 3.5 billion years ago, a revolutionary new type of bacteria evolved, cyanobacteria. These tiny organisms learned to harness the energy of sunlight to create food through photosynthesis. For them, daylight was opportunity. Darkness was starvation. This created the first, most powerful evolutionary pressure to develop a sense of time. An organism that could anticipate the dawn would have a profound advantage. It could prepare its photosynthetic machinery before the first light arrived, getting a head start. But as cyanobacteria flourished, they began to release a waste product: oxygen. Over hundreds of millions of years, this transformed the planet in what is known as the Great Oxidation Event. The atmosphere became rich in highly reactive oxygen. For the anaerobic life that had dominated the planet, this was a catastrophe. Oxygen was a poison that could damage delicate cellular machinery and DNA. This toxic new world created a second, powerful pressure for timekeeping. The clock became a crucial defense mechanism. The most vulnerable cellular processes, like DNA replication, had to be shielded. By scheduling these delicate operations for the nighttime, Cells could avoid carrying them out while also being bombarded with sunlight and producing reactive oxygen species from photosynthesis. The clock was no longer just about managing energy. It was now a tool for survival, for scheduling dangerous chemical reactions at the safest possible times. This ability to anticipate the daily cycle was so advantageous that it was conserved and passed down through every subsequent branch of the tree of life. As life became more complex, the clock was adapted for new purposes. Plants evolved clocks to turn their leaves toward the sun and to open their flowers when pollinators were most active. In animals, the clock became integrated with newly evolving nervous and endocrine systems. The clock that helps you wake up in the morning is, in a very real sense, the direct descendant of the clock that helped the first cyanobacteria find the light. It has been ticking for billions of years. It has witnessed the continents drift and the ice ages come and go. It is a living fossil within your cells, connecting you directly to the very first dawn that life ever saw. The modern conflict. For 99.99% of human history, living in sync with this ancient clock was not a choice. We rose with the sun, our activity peaked during the day, and as darkness fell, we gathered around the dim, warm light of a fire before sleeping. Our lives were tied to the planet's rhythm. Then, in the span of a historical eye blink, everything changed. In 1879, the invention of the commercial light bulb allowed us, for the first time in the history of life, to banish the night. We had, in effect, declared our independence from the sun. The core of the problem lies in how our master clock, the SCN, interprets light. To your ancient brain, bright light, especially in the blue end of the spectrum, means daytime. For millennia, the only source of this light was the sun. Now, it comes from our light fixtures, televisions, and the smartphones we hold inches from our faces. When your SCN is exposed to this bright, blue-rich light in the evening, it receives a confusing signal. The sun has set, but the brain is being told it is noon. The result is biological chaos. The SCN dutifully delays the time for bed program and suppresses the release of melatonin. Without that vital signal, your body simply doesn't get the message to wind down. You have given yourself a dose of artificial daylight, pushing your internal clock later and later. This creates a state of chronic misalignment, a condition scientists call circadian disruption. The most common form is social jet lag, the gap between your body's preferred sleep schedule and the one imposed by work or school. You might drag yourself out of bed at 6 a.m. on a weekday, but on the weekend, you sleep in until 10 a.m. This is not repaying a sleep debt. It is putting your body through a weekly time zone shift, never allowing your clock to truly stabilize. Shift work is the most extreme form of this disruption. An estimated 16% of the workforce in developed nations regularly works against their biological clock. The health consequences are well documented and severe, associated with a significantly increased risk for obesity, type 2 diabetes, cardiovascular disease, and even certain cancers. The World Health Organization has classified shift work as a probable carcinogen. This is not a statistical fluke. It is the predictable outcome of forcing a biological system to operate in a way it was not designed to. A powerful demonstration of this comes from a landmark study on mice. Researchers compared normal mice with a standard 24-hour circadian rhythm to mutant mice whose internal clocks ran on a faster 20-hour cycle. When these two groups were placed in a natural environment, the results were stark. The mice with the 20-hour clocks could not synchronize their activity with the planet's 24-hour day. Over 14 months, the normal mice outnumbered them 4-1. They were systematically selected against. Their inability to stay in rhythm with the Earth was a critical survival disadvantage. We are all, to some extent, living like those mice, trying to force our 24-hour programming to run on an artificial schedule, ignoring the rhythm written into our very being. Re-synchronizing with the planet. Understanding this conflict is the first step toward finding a solution. The solution is not to abandon modern life. It is to make small, intelligent changes to our habits, to consciously work with our ancient programming instead of against it. It is about learning to send your body the right signals at the right time. The single most powerful tool for this is light. The key is to use it deliberately. The first priority is to get bright light in the morning, as soon as possible after you wake. This can be as simple as opening the blinds or eating breakfast by a window. Better yet, it means getting outside for 10 to 30 minutes. Even on a cloudy day, outdoor light is orders of magnitude more powerful than indoor lighting. This blast of morning light sends a clear signal to your SCN. The day has begun. This one act anchors your entire 24-hour rhythm. The second half of this strategy is just as important, managing light in the evening. As darkness falls, you need to signal to your brain that the day is ending. This means curating a digital sunset. In the 2 to 3 hours before sleep, begin to dim the lights. Avoid bright overhead fixtures and opt for warm-toned lamps. Most importantly, minimize exposure to screens, whose blue light is particularly effective at suppressing melatonin. If you must use screens, use night mode, features that shift the color to the warmer end of the spectrum. The goal is to create a stark contrast between bright days and dim evenings. Beyond light, the next most powerful cue is consistency. Your circadian system thrives on routine. Going to bed and waking up at roughly the same time every single day, including weekends, is one of the most effective habits for stable energy. A consistent schedule reinforces the timing of your master clock, allowing it to more effectively synchronize the trillions of cellular clocks throughout your body. Finally, consider the timing of other behaviors. The time you eat is a powerful signal for the clocks in your digestive system. Eating a large meal late at night forces these organs to work when they are programmed to be resting. Aligning your meals with the daylight hours and allowing for an overnight fast reinforces the body's natural rhythm. Similarly, exercising in the morning or afternoon can support the daytime signal, boosting alertness and deepening subsequent sleep, while intense exercise too close to bedtime can be disruptive. None of these strategies are about perfection. They are about intention. They are about recognizing that you are a biological organism, irrevocably tied to the rhythms of the natural world. By making conscious choices about light, food, and movement, you are honoring a 4-billion-year-old legacy. You are stepping out of the chaos of artificial time and back into the steady, powerful rhythm of the planet. We began with a simple idea. There is a clock inside you, shaped by the relentless turning of our world. This clock doesn't just measure time, it embodies it. Every wave of energy, every moment of rest, is part of a grand rhythm that began with the first sunrise on a young Earth. For billions of years, life has danced to this rhythm. It is only in the last fraction of a second of evolutionary time that we have tried to write our own music. The fatigue and brain fog so common in our modern world can be understood as a form of dissonance, the sound of a body forced to play out of tune. But knowledge of this clock is not a condemnation, it is an invitation. An invitation to listen, to feel the ebb and flow of energy within you not as a nuisance to be conquered, but as an ancient wisdom trying to guide you. It is a call to see the morning sun not just as a light source, but as a biological necessity. To see the encroaching darkness not as an inconvenience, but as a vital signal for rest and repair. Your body is a living record of our planet's history. Its clock is not just telling you when to sleep, it is keeping you in tune with the cosmos. To align with it is to find your place in a rhythm that has pulsed since the beginning of time. What is one change you might consider to listen to your body's ancient clock? Feel free to share in the comments below. And if you enjoy these calm explorations into the science that connects us to the world, consider liking the video and subscribing to the channel. Earth is spinning dangerously fast and no one knows why. There are certain ideas we live with that feel as solid as the ground beneath our feet. One of those is the day. 24 hours. It's a fundamental certainty, the silent metronome for our lives. But what if that certainty was an illusion? For decades, the scientific story was that the Earth was slowing down, our days gradually getting longer. But now, something is different. Our planet is spinning faster than it has in over half a century, and we are just beginning to understand why. On June 29, 2022, the Earth finished its rotation 1.59 milliseconds faster than the standard 24 hours, setting a new record for the shortest day ever measured by atomic clocks. This isn't just a strange fact, it's a ticking clock with real consequences. Because of this mysterious speed-up, we are heading towards something that has never happened before: a negative leap second. A single, lost second that threatens to disrupt the very foundations of our digital world, from financial markets to GPS. So, what is causing our planet to accelerate? What has changed? The answer is a story of colossal forces, a tug-of-war between the chaotic dance of our planet's molten core and a surprising twist involving the climate of our entire world. This is a journey into a planetary mystery, a digital crisis that was narrowly postponed, and the discovery that our own activity is now powerful enough to physically alter the rotation of the Earth itself. The illusion of a 24-hour day. Before we explore the mystery of the speed-up, we need to look closer at the idea of the day itself. It turns out, the 24-hour day is a beautiful simplification, a neat average that hides a much more wobbly and dynamic reality. To really understand our planet's rotation, you need to know that there are two kinds of days. The first is the one we rarely talk about, the sidereal day. This is the true time it takes for Earth to make one complete 360-degree turn relative to the distant stars. That time is about 23 hours, 56 minutes, and 4 seconds. So where do the extra 4 minutes in our 24-hour day come from? They come from the second type of day, the one we all experience, the solar day. While the Earth is spinning, it's also moving on its year-long journey around the Sun. Each day, it travels about 1 degree along its orbit. This means after a full 360-degree spin, it has to rotate just a little bit more for the Sun to return to the same position in the sky. That extra rotation takes about 4 minutes, bringing the average solar day to the 24 hours we know. But even average is a key word here. The Earth's orbit isn't a perfect circle, but an ellipse. When we are closer to the Sun, our planet moves faster in its orbit, meaning it has to rotate a little further each day for the Sun to reach its highest point. During these times, a solar day can be almost 30 seconds longer than 24 hours. Our clocks ignore this, marching forward with a steady, averaged beat. For most of human history, these small changes didn't matter. But for centuries, scientists have known about a much larger force acting on our planet. A force that has been relentlessly slowing us down for billions of years. That force is the Moon. The Moon's gravity is the main reason we have tides. It pulls on Earth's oceans, creating bulges of water on opposite sides of the planet. Because the Earth spins much faster than the Moon orbits it, this rotation drags the tidal bulges ahead of the Moon. The Moon then pulls back on these bulges, creating a constant gravitational friction on the entire planet. It acts like a cosmic brake, slowly stealing rotational energy from the Earth. This effect lengthens the day by about 1.7 to 2.3 milliseconds every century. Over geological time, the impact is profound. Scientists can find traces of this history in stone. Ancient layers of sediment deposited by tides, called tidal rhythmites, act like geological tree rings. Studying them has revealed that 600 million years ago, a day on Earth was only about 21 hours long. For decades, this was the undisputed story. The Earth was slowing down. To account for this, the world's timekeepers have been adding leap seconds since 1972. inserting an extra second into our clocks to keep our ultra-precise atomic time in sync with the planet's lagging spin. This was the established order of things. A slow, predictable grind governed by the ancient dance of the Earth and Moon. And then, around the year 2020, something unexpected happened. The brakes seemed to falter. The planet hit the accelerator. The unprecedented acceleration. After decades of slowing down, the Earth suddenly started to spin faster. In 2020 alone, scientists recorded the 28 fastest days since accurate daily measurements began with atomic clocks in the 1960s. This culminated on June 29, 2022, when the planet completed its rotation 1.59 milliseconds short of 24 hours, the fastest ever documented. This shift was a shock. For years, the conversation among timekeepers was about when to add the asterisk next leap second. Suddenly, they faced a new possibility. For the first time in history, they might need to subtract 1. This negative leap second was no longer a theoretical idea, it was becoming a real possibility. The moon's braking effect hadn't stopped. So what new force was powerful enough to not only counteract the moon's pull but actually reverse the trend? Scientists turned their investigation to two of the most inaccessible places imaginable: the very center of the Earth and a strange, invisible wobble of the planet itself. The first suspect lies thousands of kilometers beneath our feet: Earth's core. Our planet is not solid. At its center is a solid inner core surrounded by a massive ocean of molten liquid metal, the outer core. The movements in this churning, liquid outer core are largely separate from the solid mantle and crust we live on. Scientists believe that shifts in the flow of the molten core can transfer momentum to the solid mantle. If the core slows down slightly, the mantle and crust must speed up to conserve momentum. This is thought to be a primary cause of short-term, random changes in the length of the day. The problem is, the core is completely hidden, so while it is a prime suspect, it remains an unproven explanation. The second theory is a phenomenon known as the Chandler wobble. Discovered in 1891, it's a small, periodic wobble in the Earth's axis of rotation, like you'd see in a spinning top. This causes the planet's poles to wander in a rough circle about 9 meters in diameter over a period of about 433 days. For over a century, this wobble has been a consistent feature of our planet's rotation. But starting around 2017, scientists noticed something extraordinary. The Chandler wobble's amplitude began to shrink dramatically, becoming almost undetectable between 2017 and 2020. This strange fading coincided almost perfectly with the Earth's sudden acceleration, leading some scientists to propose a connection. The theory is that if the Earth stops using energy to wobble, that energy might be converted into rotational speed. Think of a figure skater. If they stabilize their axis, their spin becomes faster. The disappearance of the wobble is a mystery in itself, but it's another tantalizing clue. The Earth was sending a clear signal that its internal dynamics were changing, but the full picture was still out of reach. The climate change twist. Just as scientists were grappling with the crisis of an accelerating planet, the Earth changed its story again. The trend reversed. Data from late 2022 and 2023 showed the rapid acceleration was slowing down. This revealed a profound truth. The speed-up was a temporary fluctuation, likely driven by chaotic processes in the Earth's core. It was a surge of speed that momentarily overpowered a much larger, and ultimately more significant, force. And surprisingly, that force is us. Think of an ice skater. When a skater is spinning, if they pull their arms in, their speed increases. If they extend their arms out, their speed decreases. This is due to the conservation of angular momentum. For decades, we've been observing a planetary scale version of that skater extending her arms. The cause is global warming. As human activity warms the planet, the massive ice sheets in Greenland and Antarctica are melting. This meltwater flows into the oceans and is redistributed across the globe, moving a significant amount of mass from the poles toward the equator. This movement of mass is making the Earth slightly more squashed at the poles and bulged at the equator. The water that was once concentrated near the axis of rotation is now spread out. Just like the ice skater extending her arms, this redistribution of mass is causing the Earth's rotation to slow down. This is a direct, measurable consequence of human-caused climate change. This leads to the unified theory of Earth's modern rotation, a planetary tug-of-war. On one side, you have the moon, the ancient brake. On another, the chaotic churn of the core, which can temporarily speed us up or slow us down. And now, a new player has entered the game: humanity. Through climate change, we have thrown our weight onto the side of the slowdown. The dangerous speed-up of 2020 to 2022 was real, but it was a temporary surge from the core that momentarily overpowered both the moon and the growing effect of ice melt. Now that the surge is subsiding, the true trend is re-emerging: a slowdown accelerated by global warming. In a strange twist, the melting of the ice caps has worked to counteract the core's acceleration. According to geophysicist Duncan Agnew, without the slowing effect of melting polar ice, the Earth would have spun even faster, and the need for a negative leap second might have hit us as early as 2026. The ice melt has delayed that possibility by about 3 years, pushing the potential date to around 2029 or later. We are living in an unprecedented era. For the first time, the collective actions of our civilization are measurably altering the length of a day. We haven't just changed the atmosphere, we have changed the very spin of our world. The digital apocalypse postponed? This brings us back to the threat that began this story: the negative leap second. To understand its danger, it helps to know what a normal, positive leap second is. Since 1972, timekeepers have added 27 leap seconds to our official global time, Coordinated Universal Time, UTC. This is done to keep our hyper-accurate atomic clocks from drifting too far out of sync with the Earth's slightly slowing rotation. When a leap second is added, the clock reads 23 hours 59 minutes and 59 seconds, then 23:59:60, before ticking to 0 hours 0 minutes and 0 seconds. While this has caused issues for programmers, the concept of a negative leap second is terrifying territory for our digital world. It would mean our clocks would have to skip a second entirely, jumping from 23 hours 59 minutes and 58 seconds directly to 0 hours 0 minutes and 0 seconds. The second of 23 hours 59 minutes and 59 seconds would simply cease to exist for that day. Many computer programs and networks are not built to handle time skipping a beat. The assumption that time always moves forward, second by second, is baked into the logic of our digital world. The potential consequences are staggering. High-frequency trading platforms, GPS navigation, and core internet protocols could all fail, leading to data corruption and widespread outages. It is an unprecedented situation. When the Earth was accelerating, this digital apocalypse seemed to be approaching fast, with a potential date as early as 2026. But as we've seen, the planet's return to a state of slowing, amplified by climate change, has pushed this crisis back to around 2029. We've been given a reprieve. It seems the world's timekeepers have decided to use this extra time to sidestep the problem entirely. In late 2022, the international body responsible for global timekeeping voted to effectively abolish the leap second by the year 2035. The plan is to stop these small, irregular adjustments and instead allow our official time to drift further from Earth's rotation, making a larger, more manageable correction perhaps once a century. This decision ensures the world will almost certainly never have to face the technical challenge of a negative leap second. The digital apocalypse, it seems, has been cancelled. The journey to understand our planet's changing rotation began with a mystery: After eons of slowing down, the Earth was suddenly spinning faster. We chased theories into the planet's molten core and through its invisible wobble, and we braced for the impact of a digital time bomb. But the final answer was more complex. The speed-up was just a temporary shudder from the planet's deep interior. The real story, the one defining our era, is that the long-term slowdown is back, and it's being accelerated by us. The melting of the polar ice caps is now a force so powerful that it is physically altering the length of our day. The title of this story, Earth is Spinning Dangerously Fast, was a snapshot of a very real crisis. That crisis has now been postponed. But the underlying truth it revealed is a permanent one. The 24-hour day is an illusion. Our planet is not a static rock but a dynamic, living system. Its rhythm is a symphony of competing forces. The ancient pull of the moon, the hidden turmoil of the core, and now, the undeniable weight of human civilization. We are no longer just passengers on this planet. We are now a geological force, powerful enough to change its most fundamental beat. The story of our planet is always unfolding, and as we've learned, its pace is never guaranteed. The secret clock that decides your fate. Inside of you, there is a rhythm. It is ancient and quiet. You cannot see it or hear it, but it is the silent conductor of your life. It suggests when you feel energized and when you feel tired. It releases hormones that influence your mood, your hunger, and even your strength. It is a clock tuned to the rotation of the Earth, and yet, our modern world often moves to a different beat. This is the story of that clock, of why ignoring its rhythm through late nights and distant travel has consequences more serious than just feeling tired, and how you can learn its secrets to work with it, rather than against it. If this kind of calm exploration into our own biology helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether in a city, a forest, or somewhere quiet in between, feel free to share where you're watching or listening from. The unseen force. Have you ever felt inexplicably groggy, even after what felt like a full night of sleep? Or found yourself awake at 3 a.m., staring at the ceiling? Have you experienced the deep fatigue of jet lag, where your body feels as though it exists in a different time than your mind? We often blame these feelings on stress, or diet, or simply not getting enough sleep. But what if these are symptoms of a quiet, fundamental disagreement? A disagreement between our ancient biology and the modern world we have built. This is not about productivity or willpower. It is about a biological reality as fundamental as DNA. For millions of years, life on Earth evolved to the steady, predictable rhythm of a 24-hour day. The rising and setting of the sun was not just a backdrop for evolution, it was the metronome. It was the signal that programmed our ancestors' bodies to hunt, to rest, to repair, and to grow. This internal timekeeping mechanism is known as the circadian rhythm, from the Latin words circa, meaning around, and diem, meaning a day. It is your body's internal, 24-hour clock. And this clock is not a metaphor. It is a tangible, biological machine. In 2017, the Nobel Prize in Physiology or Medicine was awarded to 3 scientists, Jeffrey Hall, Michael Rosbash, and Michael Young, who finally revealed its inner workings. They showed the world the elegant molecular gears that tick inside nearly every cell of your body, synchronizing your entire physiology with the Earth's rotation. This clock governs almost everything. It dictates the ebb and flow of hormones, the rise and fall of your body temperature, your metabolism, your immune system, and even your mood. And yet, we no longer live by the sun's schedule. We have electric lights that turn night into day. We have airplanes that carry us across time zones in hours, and work schedules that ask millions to be awake when their bodies are quietly asking for sleep. We have created a 24/7 world that is profoundly at odds with our 24-hour biology. This mismatch, this quiet war between your internal clock and your external environment, is not a minor inconvenience. There is growing evidence that this chronic misalignment is a root cause of some of the most pressing health challenges of our time. It's associated with an increased risk of obesity, diabetes, heart disease, depression, and even certain types of cancer. So, the exhaustion you feel is not just in your head. The trouble sleeping, the feeling of being perpetually off, it's a signal. It's a sign that your internal clock is struggling to find its rhythm. In this exploration, we will journey deep inside the human body. We will meet the master conductor in the brain that directs this symphony of time. We'll meet the hormones that act as its messengers, and we'll uncover the consequences of forcing this ancient rhythm to break. But most importantly, we will reveal the simple, quiet tools you can use to reset your clock, realign your body with the planet, and take back a measure of control over your energy and your health. The conductor and the symphony. To understand the story of your internal clock, we must first travel to the very center of your brain, to a tiny region of the hypothalamus. Buried deep within, just above where your optic nerves cross, lies a minuscule cluster of about 20,000 neurons. This is the suprachiasmatic nucleus, or SCN. It is small, but it is the undisputed master of your biological time. Think of the SCN as the conductor of a vast and complex orchestra. Every organ in your body, your liver, your pancreas, your heart, your muscles, has its own clock, its own rhythm. But without a conductor, they would all play to their own beat, creating a cacophony of biological noise. The SCN is what keeps them all in sync, ensuring every part of your body is playing from the same sheet music. But how does this master conductor know what time it is? Its most important cue comes from the most powerful force in our solar system, light. When light, especially morning light, enters your eyes, it does more than just allow you to see. A special set of cells in your retina sends a direct signal straight to the SCN. This signal is like the conductor tapping their baton, quietly announcing, a new day has begun. It is time to reset. This daily reset is essential because your body's natural internal rhythm isn't precisely 24 hours. For most people, it runs slightly longer. Without that morning light signal, your internal clock would drift a little later each day, quickly falling out of sync with the world around you. The SCN is the conductor. The music is a quiet, intricate dance of genes and proteins happening inside your cells. This is the very mechanism that won Hall, Rosbash, and Young the Nobel Prize. They discovered this in fruit flies, but we now know the system operates on the same principles in humans. It works through a stunningly elegant feedback loop. During the day, two key clock genes, aptly named clock and BMAL1*, partner up and switch on other genes, including one called period, or per. As the day goes on, the protein made by the *period gene begins to build up in the cell. As night falls, this per protein teams up with another protein. In humans, it's primarily a protein called Cry, for cryptochrome. Together, they are finally able to enter the cell's nucleus. Once inside, they do something remarkable. They block the activity of the very genes that created them, CLOCK and BMAL1. By shutting down their own production, they create a self-regulating cycle. As the night wears on, the per and cry proteins degrade. By morning, their levels are low enough that clock and BMAL1 can become active again, starting the entire 24-hour cycle over. It is a perfect, autonomous, molecular oscillator, ticking away day after day. This genetic rhythm is the fundamental beat to which your entire body marches. It ripples out from the SCN, sending signals that control the timing of countless other processes. And the most important of these are your hormones. Let's meet two of the lead players in this hormonal symphony, cortisol and melatonin. They operate in a beautiful, inverse relationship, a delicate dance of wakefulness and sleep. Cortisol is often called the stress hormone, but in the right context, it is the get up and go hormone. Its production is meant to follow a strict circadian pattern. Your cortisol levels naturally begin to rise in the dark, hours before you wake, reaching a peak shortly after you open your eyes. This is your body's built-in awakening signal. This morning cortisol surge helps you feel alert and focused. It raises your blood pressure slightly and mobilizes energy stores. Throughout the day, cortisol levels should gradually decline, reaching their lowest point in the middle of the night. On the other side of this dance is melatonin, often called the hormone of darkness. As daylight fades, the SCN signals a small gland in your brain, the pineal gland, to begin producing melatonin. Melatonin doesn't knock you out like a sleeping pill. Instead, it quietly signals to every cell in your body that nighttime has arrived and it is time to prepare for rest. Your body temperature begins to drop, your metabolism slows, and your brainwaves shift toward a state of sleep. Melatonin production typically peaks in the middle of the night, around 2 or 3 a.m., and then plummets as soon as your eyes are exposed to morning light. This inverse relationship is critical. When cortisol is high, melatonin should be low. When melatonin is high, cortisol should be low. This balance is the very foundation of a healthy sleep-wake cycle. In our modern world, however, this delicate dance is constantly being interrupted. Staring at a bright phone screen late at night can trick your brain into thinking it's still daytime, suppressing melatonin. Chronic stress can keep cortisol levels elevated into the evening, leaving you feeling wired but tired. It is a recipe for unease and fatigue. The orchestra does not stop there. This 24-hour rhythm governs a host of other critical functions. The release of growth hormone, vital for repair, is timed to occur during deep sleep. Your hunger hormones, ghrelin and leptin, are also under circadian control, which is why you might feel hungrier when sleep-deprived. Even your muscles have a clock. Physical performance often peaks in the late afternoon when your core body temperature is highest. This brings us back to the idea of peripheral clocks. The SCN is the master conductor, but every organ has its own clock, and these can be influenced by other cues. Scientists call these cues Zeitgebers, from the German for time givers. While the SCN's main Zeitgeber is light, the clocks in your liver and digestive system are powerfully influenced by another, the timing of your meals. When you eat, you are sending a time signal to your digestive organs. If you eat a large meal late at night, when your brain and body are winding down, you are creating a kind of internal confusion. Your brain is saying it's nighttime, but your liver is being told it's daytime. This desynchronization, this breaking of the symphony, is where the real trouble can begin. The war on the clock. For nearly all of evolutionary history, being in sync with the planet's rotation was not optional. A revealing study from the University of Manchester brought this into focus. Researchers worked with a group of mice whose internal clocks ran on a fast, 20-hour cycle, out of sync with Earth's 24-hour day. They placed these mice in outdoor enclosures alongside normal mice, forcing them to compete in a natural environment. The results were stark. Over time, the population of the out-of-sync mice plummeted. The normal mice outcompeted, outbred, and outsurvived them, to the point where the mutant mice nearly vanished. The study showed that a correctly ticking clock, in phase with the Earth, is essential for survival. Being out of sync, from an evolutionary perspective, is a profound disadvantage. We may no longer be running from predators, but this fundamental principle has not changed. Our modern lifestyle has created a world where we are all, in some way, fighting against our own biology. This constant battle manifests in several ways. The most famous example is jet lag. When you fly across multiple time zones, your body is thrown into a state of temporal chaos. Your master clock in the brain will slowly adjust to the new light-dark cycle, but it can only shift by about an hour per day. The real problem is that your peripheral clocks, in your organs, adjust at different rates. The clock in your liver might shift with your new meal times, while the clock in your muscles lags behind. The result is not just that your body is on the wrong time zone. It's that your internal organs are all on different time zones from each other. This internal desynchrony is what causes the profound fatigue, digestive issues, and cognitive fog of jet lag. You feel terrible because your body has temporarily become an orchestra without a conductor. If jet lag is an acute event, then shift work is a chronic one. Millions of people, doctors, nurses, factory workers, first responders, are required to be awake when their biology is programmed for sleep. This is not just a matter of feeling tired. The World Health Organization's International Agency for Research on Cancer has classified night shift work that involves circadian disruption as a probable carcinogen. It is a quiet but serious statement. Why? Because chronically forcing your body to operate against its natural rhythm has long-term consequences. Studies consistently link long-term shift work to a significantly higher risk of cardiovascular disease, as well as metabolic syndrome, a cluster of conditions including obesity and high blood sugar. This makes sense when you consider that shift workers are often eating when their metabolism is at its slowest, which can lead to insulin resistance and, eventually, type 2 diabetes. The cancer connection is particularly alarming. Our clock genes also play a role in repairing DNA damage. When these genes are dysregulated by constant circadian disruption, combined with the suppression of nighttime melatonin, a hormone with antioxidant properties, the body's natural defenses can be impaired. But you do not have to be a shift worker to experience this. Many of us suffer from a more subtle version called social jet lag. The term, coined by researcher Till Roenberg, describes the mismatch between your sleep schedule on workdays and your sleep schedule on free days. If you wake at 6:30 a.m. on weekdays but sleep in until 10 a.m. on Saturday, that 3.5-hour difference is the equivalent of flying from New York to San Francisco every single weekend. While it might feel like catching up, research shows this pattern is disruptive. Even this less extreme form of misalignment is associated with negative health outcomes, including higher cholesterol and an increased risk for metabolic disease. The reason is the same: consistency is important. When your sleep-wake cycle is erratic, your internal clocks never get a chance to firmly anchor themselves. Every Monday morning becomes a small-scale jet lag experience. We have, in many ways, forgotten our ancient clock, and the consequences are written in our rising rates of chronic disease. But it is not a lost cause. We can learn to listen to it again. Reclaiming your fate. This story is not meant to be one of unavoidable fate. It is about understanding. The beauty of the circadian system is that while it is ancient, it is also designed to be reset. It is constantly looking for cues from the environment to stay in sync. By consciously providing the right cues, you can move from a state of conflict to a state of harmony. You can become the conductor of your own symphony. The most powerful tools for this are simple, and have been available to us for millennia. It all comes down to a few fundamental principles. Principle 1. The role of light, **. Light is, without a doubt, the most powerful signal for your master clock. Getting this right is the single most important thing you can do for your rhythm. The method is simple. Get bright light exposure within the first 30 to 60 minutes of waking up. This does not mean staring at the sun. It means going outside for a 10 to 30-minute walk. Even on a cloudy day, the intensity of natural outdoor light is far greater than indoor lighting. This morning light sends a powerful, start the day, signal to your SCN, firmly anchoring the beginning of your 24-hour cycle. If you live in a place with dark winters or cannot get outside, a 10,000 lux light therapy lamp can be an effective substitute. The second half of this principle is just as important. Avoid bright light in the 2 to 3 hours before bed. In the evening, your brain expects darkness to signal the release of melatonin. Bright overhead lights, or the blue light from phones and computers, send a confusing signal. It's still daytime. This can delay melatonin release and push your rhythm later. The solution is to create a kind of digital sunset. Dim the lights in your home. Switch devices to night mode or, even better, put them away for the last hour before bed. Principle 2. The timing of fuel, **. The peripheral clocks in your organs listen to your meal schedule. Eating is a powerful Zeitgeber or time cue for your metabolic system. To keep your body in sync, it helps to align your eating window with your active period. Consuming most of your calories during the day, when your body is primed for digestion, works with your rhythm. Eating a large meal late at night forces your digestive system into overdrive when it should be resting, leading to desynchronization between your brain's clock and your body's clocks. A powerful strategy to align your eating with your clock is time-restricted eating, TRE. This is not about what you eat, but when you eat. By consolidating your meals into a consistent 8 to 10 hour window each day. For example, eating only between 9 a.m. and 7 p.m. You give your digestive system a long, predictable fasting period each night. This allows your metabolic organs to switch over to a state of repair, a process known as autophagy. This helps resynchronize the peripheral clocks and has been shown to improve insulin sensitivity. The key is consistency, trying to keep your eating window roughly the same every day. Principle 3. The importance of consistency, **. Your circadian rhythm thrives on routine. It is a clock, and clocks work best when they are set to a predictable schedule. This means going to bed and waking up at approximately the same time every day, even on weekends. This may be the most challenging principle for many, but its impact is profound. When you maintain a consistent sleep-wake schedule, you eliminate social jet lag. This consistency provides a stable anchor for your SCN, allowing it to send clear signals to the rest of your body. You will fall asleep more easily and wake up more refreshed because your body finally knows what to expect. Principle 4. Movement and temperature, **. Other cues can help guide your clock. Regular exercise, especially when done at a consistent time, helps to reinforce your rhythm. Morning or early afternoon exercise tends to be most beneficial. Intense exercise late at night can sometimes be disruptive, as it can raise your core body temperature when it should be falling. Temperature itself is a core part of your circadian rhythm. Your body temperature naturally drops at night, a crucial signal for sleep. You can help this process by taking a warm bath or shower an hour or two before bed. The subsequent cooling of your body mimics the natural temperature drop that precedes sleep. Keeping your bedroom cool is also critical. These are not rules about perfection. They are about intention. They are about recognizing that we are biological creatures, tuned to the rhythms of the natural world. By sending your body these quiet signals, you are not just hacking your sleep. You are engaging in a quiet act of biological respect. You are making peace with the ancient clock that ticks within you. Living in sync with this rhythm is one of the most powerful things you can do for your health. If you found this journey into your body's quiet clock valuable, please consider subscribing and sharing this video. The more people who understand this fundamental aspect of our biology, the healthier our world can be. And let us know in the comments, what is one small change you might make this week to listen to your own clock? We began this journey with an invisible clock, an unseen force that dictates the rhythm of your life. We now know this clock is no mystery. It is the suprachiasmatic nucleus, the master conductor in your brain. Its music is the elegant, Nobel Prize-winning dance of clock genes ticking away inside your cells. Its messengers are the hormones, like cortisol and melatonin, that manage the symphony of your daily life. We've learned that this clock was forged by evolution to synchronize us with the 24-hour rotation of our planet. And we've seen the consequences of moving against this rhythm, in the evolutionary failure of mice with broken clocks, in the chaos of jet lag, and in the long-term health toll paid by those who work against the night. We've seen how even the subtle social jet lag of our modern weeks is associated with an increased risk of disease. But this story does not end in despair. It ends with empowerment. The knowledge of this clock is not a sentence, but a key. It unlocks a new understanding of health, one that looks beyond just calories and exercise, and looks at a third, crucial dimension: timing. You now know the principles. You know that morning light is the anchor for your day. You know that aligning your meals with your active hours prevents metabolic confusion. And you know that consistency is the bedrock upon which a stable rhythm is built. The secret clock that decides your fate is not some external, uncontrollable force. It is inside you. It is a part of you. And while it was programmed by an ancient world of sunrises and sunsets, it is responsive. It is listening. It is waiting for your cues. By honoring its rhythm, by sending it clear and consistent signals, you are not just aiming for better sleep or more energy. You are tuning your own body to the grand, cosmic rhythm of the earth itself. That ancient clock is ticking right now. It waits patiently for us to listen. The worldwide system that's always messing you up. There is a dissonance many of us feel, a kind of jet lag, without travel, that suggests we are living on a schedule not entirely of our own making. This is not an imagined phenomenon. It is a design feature of a global system conceived nearly 150 years ago. A system built to impose order, but which quietly disrupts our sleep, our health, and our economies. Its story begins with the simple rotation of the Earth, but it unfolds across a very complicated map. This is a journey through a system we all inhabit, but few truly understand, a story of an attempt to tame time, and how, in many ways, time continues to elude our control. The relatable problem, our clockwork chaos. The time zones of the world exist as a constant, low-grade source of friction. A meeting invitation arrives, asking for a call at 2 p.m. Eastern Standard Time, and a calculation begins, complicated by the fact that one location observes daylight saving and another does not. A message sent across continents is met with silence or a frustrated reply, because the recipient's local time is 4 a.m. Even with tools and careful checks, a quiet uncertainty can persist. This is the subtle texture of life in a globally connected age. A world where teams are scattered across continents, families live in different countries, and the release of media is determined by a clock halfway across the planet. We are expected to operate in a seamless digital world, yet we find ourselves stumbling over these invisible, arbitrary lines that govern our daily rhythms. The problem is more than just a matter of scheduling. It is a more fundamental disconnect. It is the experience of waking when it is still dark outside, or preparing for sleep while the sun is still bright. It is the biannual ritual of adjusting every clock, a collective, self-imposed temporal shift that leaves populations feeling groggy and out of sync for days. Some studies have linked the abrupt spring forward into daylight saving time to a notable, temporary spike in serious health events like heart attacks, a consequence of widespread sleep deprivation. We have come to accept this condition as normal. We use world clock applications, memorize acronyms, PST, SET, JST, and we learn to navigate our temporal miscalculations. But this friction may be a symptom of a much larger condition, rooted in a well-intentioned but perhaps outdated attempt to standardize the planet. A system that promised to put the world on the same page has, in some ways, left us feeling perpetually out of sync. To understand why the clock on the wall can feel like an adversary, we must look to a time before that clock mattered. A time when the only clock was the sun in the sky. And we must examine the invention that made it all so complicated, the train. The simple origin story, taming a spinning planet. Before the middle of the 19th century, the idea of a time zone would have seemed abstract. Time was a local phenomenon. Noon was understood as the moment the sun reached its highest point in the sky. It was simple, intuitive, and sufficient for a world that moved at the speed of a horse. Every city and town operated on its own, local solar time, creating a complex and beautiful patchwork of times. When it was 12 o'clock in Washington, D.C., it was 12:02 in Baltimore and 11:50 in Richmond. In the United States alone, there were hundreds of different local times, and this was largely unimportant. Then came the Industrial Revolution, and with it, the railroad. Humanity began to move at the speed of steam, and this new velocity created a new and dangerous problem. A train timetable from the 1870s might show a departure from City A at 10 a.m. and an arrival in City B, 50 miles away, at 11 a.m. But City B's 10 a.m. could be several minutes different from City A's. When another train travels in the opposite direction on its own local time, the potential for disaster becomes immense. Railroad timetables became exercises in temporal complexity, with dozens of different railroad-specific time standards in use across North America. The system was untenable. The engine of modern commerce was being throttled by the chaos of 1,000 different noons. From this problem, a new kind of thinking emerged. Visionaries like Charles F. Dowd, a school principal, and Sir Sandford Fleming, a Canadian railway engineer, saw in this mess a simple, elegant solution. Their logic was grounded in the physics of our planet. The Earth rotates 360 degrees approximately once every 24 hours. A simple division reveals a key number, 15. Dividing 360 degrees of longitude by 24 hours yields 15 degrees per hour. The idea was revolutionary in its simplicity: to slice the world into 24 distinct wedges. Each wedge would be 15 degrees of longitude wide, and within it, every clock would be synchronized. As one crossed from one wedge to the next, the time would shift by precisely 1 hour. No more minutes of difference, no more confusion, only clean, standardized, 1-hour blocks. To make this global system work, it needed a single starting point, a zero line. This led to the International Meridian Conference in Washington, D.C., in October 1884. At the request of U.S. President Chester A. Arthur, 41 delegates from 25 nations gathered to choose a prime meridian, a single, zero of longitude and standard of time reckoning throughout the world. After deliberation, they selected the meridian passing through the Royal Observatory in Greenwich, England. There were practical reasons for this. The British Empire's vast naval and commercial networks meant that over 2/3 of the world's ships already used Greenwich as a reference point. With that decision, the world was officially synchronized. Greenwich Mean Time, or GMT, became the anchor. Every other time on Earth would be defined by its offset from this single point. Noon would strike at Greenwich when the sun was directly overhead, and the rest of the world would follow in an orderly, 24-hour procession. It was a triumph of logic, a global agreement designed to bring order to industrial modernity. The plan was perfect. The mathematics were clean. The map should have been a set of straight, parallel lines. But human geography, politics, and national identity were about to intervene. And that is when the map became messy. The complication and the mess, when lines on a map get weird. If the theory of time zones is a pristine mathematical equation, the reality of the world map is that equation redrawn and overwritten. The neat 15-degree slices of the globe were a logical starting point, but they immediately encountered the inconvenient reality of human settlement and politics. A straight line on a map might divide a country, or separate a city from its own suburbs. So, the lines began to bend. Nowhere is this defiance of pure geometry more apparent than in China. Geographically, this vast nation spans 5 theoretical time zones. Yet, since 1949, all of China has operated on a single, official time. Beijing time, UTC+8. This was a political decision, intended to foster a sense of national unity. The practical consequences are surreal. In far western regions like Xinjiang, solar noon, the point where the sun is highest, can occur as late as 3 p.m. on the clock. Life in the West is effectively offset, with work and school starting 2 hours later than in Beijing, though the clock reads the same. In some areas, an unofficial local time is still used, creating a dual time system where the answer to "what time is it?" can depend on who you ask. Then there are the nations that decided a full hour was too coarse an adjustment. India, another very large country, straddles two natural time zones. Instead of choosing one or dividing itself, it compromised. The entire nation runs on UTC plus 5:30. This half-hour offset splits the difference, ensuring no part of the country is too far out of sync with the sun. It is a pragmatic solution, but it belongs to a family of temporal outliers. Afghanistan uses UTC plus 4:30. Iran is on UTC plus 3:30. Newfoundland, in a display of its unique identity, remains on a half-hour offset from the rest of Atlantic Canada. And then there is Nepal. Not content with a half-hour, Nepal chose to assert its identity with even greater precision. The entire country is set to UTC plus 5:45. This unusual 45-minute offset was chosen because it aligns more closely with the local mean time of its capital, Kathmandu. Australia, too, has its own temporal curiosity. A small area on the border of Western and South Australia, including the town of Eucla, unofficially observes UTC plus 8:45, creating a tiny, self-contained 45-minute time zone. Perhaps the most pronounced example of a time zone shaped by politics over geography is Spain. On a map, Spain sits on the same longitude as the United Kingdom and Portugal. Logically, it should be on Greenwich Mean Time, and for a period, it was. But in 1940, General Francisco Franco advanced the nation's clocks by 1 hour. While often viewed as a gesture of solidarity with Nazi Germany, the move was also part of a broader strategy for wartime coordination and reflected economic ties with continental Europe. The war ended, the regime fell, but the time zone was never changed back. The result is a country living in a state of perpetual, low-grade social jet lag. The sun rises and sets an hour later by the clock than it should, a fact which has profoundly shaped Spanish culture, from famously late dinner times to long work days. This political gerrymandering of time culminates at the most unusual line on the planet, the international dateline. In theory, it is a straight line at 180 degrees longitude. In reality, it zigs and zags dramatically to avoid splitting island nations into two different calendar days. The most extreme deviation occurred in 1995. The island nation of Kiribati, a sprawling archipelago, was split by the dateline, meaning the eastern and western parts of the country could only conduct business on 4 shared weekdays. In response, Kiribati's government unilaterally shifted the line eastward. This move placed the entire country on the same calendar day and, in its line islands, created the UTC plus 14 time zone. This made Kiribati's eastern islands one of the first places to greet the new day, a status it marketed for the year 2000 celebrations. These are not just strange facts. They are illustrations of a fundamental tension at the heart of our timekeeping system, a conflict between the clockwork of the planet and the messy, often irrational demands of the people who live on it. This system, designed for order, has been twisted into a reflection of our political histories and our national identities. And these messy lines have consequences that reach far beyond scheduling. The surprising consequences, the hidden costs of our clock. The complex state of the map is more than an intellectual curiosity. This system, with all its compromises and absurdities, has a tangible and measurable impact on our lives. It begins with a concept known as social jet lag. Coined in 2006 by chronobiologist Till Ronenberg, social jet lag describes the mismatch between the body's internal biological clock, the circadian rhythm, and the social clock imposed by work, school, and the local time zone. Forcing an awakening at 6 a.m. on a weekday, against the body's natural inclination, followed by sleeping in on the weekend to catch up, is a familiar pattern. To the body, this weekly shift is equivalent to a flight across several time zones. It is a chronic stressor, and research has linked it to a host of health problems. Studies suggest that for every hour of social jet lag, the risk of being overweight increases, and it is associated with a greater likelihood of metabolic issues, heart problems, and mood disorders. This problem is physically embedded in the map. A compelling body of research shows that living on the western edge of a time zone can be detrimental to health. Because the sun sets later in the west of a zone, people there tend to go to bed later. Yet, social schedules like work and school often remain uniform across the entire zone. The result is that people on the western edge are chronically more sleep-deprived. One major study found that individuals on the late sunset side of a time zone boundary get, on average, 19 minutes less sleep per night, which accumulates to over 115 hours of lost sleep per year. This chronic sleep debt has been correlated with higher rates of obesity, an increased risk of heart attack, and even economic effects, with wages tending to be slightly lower, potentially due to lower productivity from fatigue. One's geographic location can be at odds with one's own body clock. And then there is the jet lag that comes from travel. This is a direct confrontation with the planet's spin. The circadian rhythm is a deeply ingrained 24-hour cycle, tuned to the light and dark patterns of a home environment. Flying across multiple time zones desynchronizes this internal clock from the new environment. The sun may signal morning, but the body's clock insists it is the middle of the night, leading to fatigue, insomnia, and digestive issues. The direction of travel makes a significant difference. Flying eastward is generally harder on the body than flying westward. An eastward flight is a shorter day, forcing the body to advance its clock and attempt to sleep before it is ready. Our natural circadian rhythm tends to be slightly longer than 24 hours, making it easier to delay sleep, as when flying west, than to advance it. The general rule is that it takes approximately 1 day to recover for every 1-hour time zone crossed. The most widespread example of this forced desynchronization is daylight saving time, DST. Twice a year, millions of people are subjected to a mandatory 1-hour time shift. Originally proposed to save energy, a rationale many modern studies find inconclusive, the practice is essentially a government-mandated dose of social jet lag. The health effects are well documented. In the days following the spring forward, hospitals often report a spike in heart attacks and strokes. Traffic accidents increase. The fall back is not benign either, and is often associated with an increase in mood disturbances. Chronobiologists are nearly unanimous in their view that these shifts are more harmful than beneficial, and the fact that some regions function perfectly well without them is a reminder that this biannual disruption is a choice, not a necessity. The system born of a desire for order has created a world of hidden stresses. It misaligns our biology with our social lives and subjects us to biannual shocks to our health. We are in a constant state of negotiation with the clock on the wall, a clock that often tells a time at odds with the sun in the sky and the rhythms in our own cells. This has led some to ask a radical question. What if we did away with the system altogether? The what if, or the future, a world on one clock? Given the complexity and the health consequences of our current system, a bold idea has gained new traction: the abolition of time zones in favor of a single, universal time. The proposed system is Coordinated Universal Time, or UTC. It is already the standard used by pilots, scientists, and financial markets for global coordination. The concept is simple. Every clock, everywhere, would display the exact same time. 1400 in London would also be 1400 in New York, Tokyo, and Sydney. The primary benefit would be the immediate elimination of temporal confusion. Scheduling an international meeting would become as simple as saying, Let's meet at 1500 Coordinated Universal Time. No conversion, no mental math, no DST-related errors. For global business and logistics, it would be a revolution in simplicity. In practice, while the clock on the wall would be universal, local schedules would still adapt to the sun. In London, 1400 Coordinated Universal Time is mid-afternoon. In New York, that same 1400 Coordinated Universal Time would be morning, perhaps the time of arrival at an office. In Beijing, 1400 Coordinated Universal Time would be late evening. We would simply learn to associate different activities with different numbers on the clock based on our longitude. Proponents argue this is merely a software update for our social conventions, a rational step for a global species. It would align our global systems with a single standard, while allowing local cultures to maintain their natural, sun-based rhythms. The largest hurdle, however, may be psychological. It feels counterintuitive to divorce the numbers on a clock from the experienced cycle of day and night. The terms AM and PM would become meaningless. It could feel like a profound detachment from our most fundamental connection to the planet's rhythm, creating a new layer of cognitive dissonance. The debate mirrors the arguments from the 1880s, when local towns protested the idea that they would have to eat, sleep, work, and marry by railroad time. While a global switch to UTC remains a distant possibility, the movement to abolish daylight saving time is gaining momentum, with many scientific and medical organizations arguing for a permanent return to standard time, which better aligns with our natural biology. These debates demonstrate that our system of time is not an immutable law of nature. It is a human invention. We built it, we have altered it, and we have the power to change it again. From a planet spinning in the void, to a train on a track, to a line on a map that influences when we eat dinner. The story of time zones is the story of our attempt to impose human order on a cosmic cycle. It began with a logical idea to slice the world into 24 predictable pieces. But that logic collided with politics, culture, and the inconvenient fact that our bodies have their own clocks, shaped by millions of years of evolution under a rising and setting sun. The result is the system we have today. A patchwork of compromises, a map of historical events and political statements. It is a system that creates invisible frictions in a globalized world and wages a quiet, persistent war on our health. It is a profoundly human system, brilliant in its ambition, flawed in its execution, and constantly in flux. The next time you feel that sense of being out of sync, it is worth remembering that this is not a personal failing. It is a feature of a 150-year-old agreement, one that is constantly being renegotiated by technology, convenience, and our own biology. It leaves us with a quiet, fascinating question. If we were to design time again today, would we do a better job? The 1,000 miles per hour speed gap that bends our weather. Go ahead, look out your window. Everything seems pretty still, right? The ground feels solid, stable, motionless. But what if I told you that's all a massive illusion? Because right now, every single one of us is a passenger on a giant sphere, spinning through the vastness of space at a ferocious speed. And here's the really wild part. How fast you're moving depends entirely on where on this sphere you happen to be standing. See, the same physics that makes your backyard feel so peaceful is the exact same physics that governs the entire planet. And when you zoom out to a planetary scale, words like quiet and still just don't apply. Our world is shaped by invisible forces and colossal energies that make anything humanity can build look like a child's toy. These forces are born from simple geometric facts, but they cascade into storms the size of continents and currents that chart the course for our oceans. We live our lives mostly unaware of these massive planetary engines. We feel the rain, but not the giant mechanism that brought it. We feel the wind, but not the invisible hand that bent it off course. Today, we're pulling back the curtain on one of the most powerful of these engines. It all starts with a single number, and it explains so much about our world, from the paths of ancient explorers to the terrifying beauty of a hurricane. Right now, you are moving fast, but how fast depends on your address. If you're near the equator, say in Quito, Ecuador, you're currently rocketing through space at over 1,000 miles per hour. But if you were to magically transport to the North or South Pole, you'd be doing little more than just slowly spinning in place. This 1,000 mile per hour speed gap between the equator and the poles is the invisible engine that powers our planet's weather. It is the secret architect behind the beautiful, terrifying spiral of a hurricane. But how? How can a simple difference in speed, something we can't even feel, bend our entire atmosphere into the most powerful storms in the solar system? We're about to connect the dots, from a quiet spot on a map to the fury of a Category 5 hurricane. And it all starts with the simple fact that our planet spins. The spinning planet, a tale of two speeds. To really get this, we need to shrink ourselves down and look at our home from a distance. Earth rotates as one solid object, making a full turn about once every 24 hours. That part's pretty straightforward. But the consequences of that simple spin? Anything but. Think of an old-school vinyl record on a turntable. Now, imagine two tiny ants on it. One ant is near the center label, and the other is way out on the edge. When you hit play, the record makes one full rotation. Both ants complete their circle in the exact same amount of time. But think about the asterisk distance they traveled. The ant near the center traced a tiny little circle. It barely moved. The ant on the edge, though, had to travel the entire massive circumference of the record to get back to where it started. To cover that much more ground in the same amount of time, it had to be moving way faster. Our planet is that record. And we are the ants. At its widest part, the equator, the Earth's circumference is a whopping 24,901 miles. To cover that distance in 24 hours, a point on the equator has to move at about 1,038 miles per hour. We'll just call it 1,000 for simplicity's sake. Now, let's travel north. Say, to Philadelphia, at 40 degrees latitude. The circle a person in Philly makes over 24 hours is smaller, only about 19,000 miles. To cover that shorter distance in the same 24 hours, their speed is slower, around 792 miles per hour. That's already a 200 miles per hour difference from the equator. Let's keep going, all the way to the North Pole. Here, you're standing right on the axis of rotation. In 24 hours, you don't travel thousands of miles. You just spin. You turn 360 degrees, right on the spot. Your speed is basically zero. This is the 1,000 miles per hour speed gap. The difference between the land screaming through space at the equator and standing almost still at the poles. And this isn't just a fun piece of trivia. It's the source of a phantom force that steers our entire atmosphere. Of course, the reason you don't feel like you're on a rocket ship is that everything around you, the air, the oceans, the buildings, is also moving at that same speed. It's all moving together. It's like being on a plane cruising at 500 miles per hour. You can walk around, pour a drink, and feel perfectly normal because you, the plane, and the air inside are all in the same moving system. The magic, and the chaos, begins when something starts to move across these different lanes of speed. What happens when you take a chunk of air from a slow lane near the pole and send it towards the fast lane at the equator? This is where things get weird. Welcome to the world of apparent forces, and the birth of something called the Coriolis effect. The Coriolis effect, the phantom curve. Okay, the Coriolis effect is one of the most misunderstood ideas in physics. It's not a real force that's pushing on things. It's an asterisk apparent force. It's a ghost, and it only shows up when you try to move in a straight line across something that's spinning. The best way to feel this is to head to a playground. Picture this. You and a friend are on a merry-go-round, sitting on opposite sides. It starts spinning, counterclockwise. You try to roll a ball straight to your friend. You give it a good push, aimed perfectly. But it never reaches them. From your point of view on the ride, the ball seems to curve away to the right, missing your friend completely. It looks like some invisible force pushed it sideways. But now, imagine someone is standing on the grass watching all of this. From their stationary view, the ball traveled in a perfectly straight line. It never curved. What really happened was your friend, the target, rotated out of the way while the ball was in the air. The force that curved the ball only existed in your spinning world. That phantom push is the Coriolis effect. Now, let's scale that up to the size of a planet. Earth is our merry-go-round, and the ball is anything not nailed down, a puff of air, an ocean current, even a long-range missile. Let's take a pocket of air from the North Pole. It's basically standing still. Now, say a low-pressure zone opens up to the south, and this polar air starts moving toward the equator. It's trying to go in a straight line south. But the ground underneath it is rotating eastward, faster and faster the further south it goes. From the ground's perspective, the southward moving air, which had zero eastward speed to begin with, seems to lag behind. It looks like it's drifting to the west. A straight path on a spinning sphere becomes a curved path. And in the northern hemisphere, that curve is always to the right. Now, let's flip it. Imagine a puff of air at the equator, blazing along at 1,000 miles per hour to the east with the ground. Something pulls it north. It carries all that eastward momentum with it. But as it moves north, it travels over ground that is rotating slower. This fast-moving air basically overtakes the slow-moving ground below. The result? It appears to get deflected to the east. Once again, to the right of its direction of motion. So, no matter which way you're headed in the northern hemisphere, north or south, any long-distance movement gets a ghostly nudge to the right. In the southern hemisphere, the exact opposite happens. Since the Earth spins clockwise when viewed from the South Pole, everything gets deflected to the left. This perfect, beautiful symmetry is a direct result of the way our planet spins. This has real-world consequences. When military snipers calculate a shot over a mile, they have to account for the Coriolis effect. The Earth will literally rotate a few inches underneath the bullet as it flies. If you don't account for it, you miss. The strength of this phantom force is strongest at the poles and weakest at the equator. In fact, right on the equator, it's zero. This little detail is the reason why the most powerful storms on Earth can't survive in the one place you'd expect them to be born. So now we have our mechanism. A planet with a massive speed differential, creating a phantom force that deflects anything that moves long distance. What happens when you apply this strange, curving influence to the biggest fluid system on our planet? Our atmosphere. Painting the wind. How the speed gap creates global breezes. If the Earth didn't rotate, our weather would be simple and brutal. The equator gets the most sun, so it's hot. The poles are cold. Hot air rises, cold air sinks. You'd have a constant, howling gale blowing from the poles straight to the equator. Life would be difficult. But our Earth does rotate. And that 1,000 miles per hour speed gap, through the Coriolis effect, throws a beautiful wrench into that simple system. Let's follow the air. At the equator, hot air rises, creating a low pressure belt. High in the atmosphere, it starts to move toward the poles. Immediately, the Coriolis effect grabs it. In the northern hemisphere, this air is deflected to its right, to the east. It becomes a high-altitude westerly wind. By the time this air gets to around 30 degrees latitude, it has cooled and piled up, and it sinks. This sinking air creates a high-pressure belt, which is why a lot of the world's big deserts, like the Sahara, are parked right at this latitude. Once at the surface, the air splits. Some goes toward the pole, but let's follow the air that heads back to the equator to finish the loop. As this surface air moves south, the Coriolis effect deflects it to the right again, this time to the west. So, instead of a wind blowing straight south, We get a reliable, steady wind blowing from the northeast to the southwest. These are the trade winds. For centuries, these winds were the highways of the age of sail. Mariners learned they could sail south from Europe, catch these winds, and get a reliable push all the way to the Americas. Christopher Columbus absolutely relied on this. To get home, they had to sail north until they hit the next belt of winds, the westerlies. This is the air that flows poleward from the 30-degree high-pressure zone. As it moves north, the Coriolis effect bends it to the right, creating the westerly winds that dominate places like Europe and North America. This elegant, three-cell system in each hemisphere is all a direct result of the planet's spin breaking up one giant, simple wind pattern. For thousands of years, sailors were using the 1,000 miles per hour speed gap. They didn't know the physics, but they knew the winds blew in predictable curves. They were reading a weather map drawn by the spin of the Earth itself. And this bending of the wind does more than just help ships sail. It's the first step in organizing weather on a truly terrifying scale. Because when this curving airflow meets the perfect fuel source, a patch of warm ocean water, it starts to build something monstrous. We just saw how a simple geometric fact created the winds that powered global exploration and literally shaped human history. If you're having that aha moment, seeing how these deep principles connect to our world in surprising ways, this is what we do here. We track down the hidden physics that explains our reality. So if you want to keep unraveling the science that shapes our world, take a second to subscribe and hit that bell. Now, let's get back to the storm. The main event, forging a hurricane. Alright, all the pieces are on the board. We have the speed gap. We have the Coriolis effect that bends the wind. Now, let's build a hurricane. First, you need fuel. Hurricane fuel is warm ocean water. At least 80 degrees Fahrenheit, 26.5 degrees Celsius. Going down about 150 feet. This is why hurricanes are a tropical thing. This warm water evaporates, pumping huge amounts of moisture and heat energy into the air. This is the raw power. Second, you need a little spark. A pre-existing disturbance. A little wave in the atmosphere. Maybe a cluster of thunderstorms moving off the coast of Africa. Just something to create a weak spot of low pressure. On a non-spinning planet, air would rush straight into that low pressure spot, fill it up, and the storm would fizzle out. End of story. But on our spinning Earth, the story is just getting started. As air from all around rushes toward that low pressure center, the Coriolis effect grabs it. In the northern hemisphere, air from the north, moving south, gets bent to its right, west. Air from the south, moving north, gets bent to its right, east. Air from the east, moving west, gets bent to its right, north. Air from the west, moving east, gets bent to its right, south. Do you see what's happening? No matter where it comes from, the air can't go straight to the center. It keeps getting nudged sideways. The result of all those constant right-hand turns is that the whole mass of air begins to rotate around the center. This is the birth of the cyclonic spin, always counterclockwise in the northern hemisphere. In the southern hemisphere, it's a perfect mirror image. The leftward nudge creates clockwise spinning storms. Every single satellite picture of a hurricane is the planet's signature, written in the clouds. Once this rotation starts, a powerful feedback loop kicks in. The spin gets more efficient at sucking in warm, moist air. As that air spirals inward and rises, the water vapor condenses, releasing a truly colossal amount of heat. This heat warms the core, which lowers the pressure even more. Lower pressure pulls in air faster, creating stronger winds. Stronger winds get bent harder by the Coriolis effect, making the rotation even tighter. Heat, lower pressure, faster winds, tighter spin, more heat. That is the engine of a hurricane. This creates the most iconic and eerie feature of a monster storm, the eye. As the winds get faster and the rotation tightens, The air is moving so fast it can't make that final turn into the dead center. Centrifugal force, the same thing that pushes you out on a merry-go-round, becomes so strong it balances the low-pressure pull. The air simply can't get there. Instead, it forms a wall of the most violent winds and rain, the eye wall. And inside that wall, in the eye itself, air from high up in the atmosphere sinks. Sinking air is dry and warm. So, in the dead center of the most violent storm on the planet, you find an oasis of creepy calm, clear skies, and light winds. A hole in the storm, held open by the sheer fury of the spin around it. And remember how the Coriolis effect is zero at the equator? That's why hurricanes can't form there. Even with all the warm water fuel, there isn't enough of a spin to get the rotation started. And for the same reason, a hurricane can never cross the equator. The opposing forces would tear it apart. The equator is a planetary, no-go zone for cyclones. The 1,000 miles per hour speed gap isn't just a small part of a hurricane. It's the essential organizing principle. It is the invisible architect that sculpts a mess of thunderstorms into a swirling, self-sustaining monster. The global conveyor belt, oceans in motion. The atmosphere isn't the only thing that feels the ghostly touch of the planet's spin. The same rules apply to the oceans, just on a much slower, more massive scale. The big global winds, like the trade winds and westerlies, are themselves a product of the Coriolis effect. As they blow across the ocean, they drag the water with them. But that moving water is also deflected by the Coriolis effect, to the right in the north, to the left in the south. When you combine this with the continents acting as giant walls, you get massive, circular currents called ocean gyres. In the North Atlantic, you get a huge, clockwise rotating gyre. This includes the Gulf Stream, that famous river of warm water flowing up the US East Coast and then over to Europe. It's a huge reason why London is milder than, say, northern Canada, even though they're at similar latitudes. These gyres are the planet's circulatory system. They're a global conveyor belt, moving immense amounts of heat from the equator to the poles, making our planet more habitable. And there's a modern, unfortunate consequence. The centers of these gyres are calm and stable, which allows floating debris to collect. The infamous Great Pacific Garbage Patch is stuck in the middle of the North Pacific Gyre, a swirling monument to the power of these planet-spanning currents. Debunking the myth, the bathtub drain. Okay, we have to talk about the toilet. Because if you've heard of the Coriolis effect, you've probably heard it's why water drains one way in the northern hemisphere and the opposite way in the southern. It's a great story. And it is completely, 100% false. Yes, the Coriolis effect is real. But it is incredibly weak. It's only noticeable over huge distances and long time periods, like continent-sized air masses and ocean basins. A bathtub or a toilet is just tiny. The force acting on that little bit of water is so minuscule it's completely drowned out by other factors. The shape of the sink, how you poured the water in, the design of the drain, any of those will have 1 billion times more influence than the rotation of the Earth. You can easily make the water drain either way just by giving it a little swirl. The toilet myth is a classic case of taking a real science principle and applying it at a scale where it just doesn't matter. It helps us appreciate the true scale we're talking about here. This isn't a household force, it's a global one. It doesn't shape the water in your sink, but it absolutely shapes the world outside your window. We started with a simple fact. The ground beneath the equator is moving at over 1,000 miles an hour, while the poles are standing still. A speed gap born from the simple geometry of a spinning ball. From that one fact, we saw how a phantom force emerges, a ghostly nudge that only exists because we're on a spinning ride. We saw how that nudge grabs our atmosphere, bending straight winds into the great curved highways that powered the age of sail. We saw how that same bending force takes a disorganized bunch of thunderstorms and sculpts it into the terrifying, perfect spiral of a hurricane, with a calm eye held open by the sheer rotational fury of the storm. And we saw how it steers our oceans into massive gyres, a global conveyor belt for heat that regulates our climate. It's all connected: the speed, the spin, the curve, the wind, the storm, the current. One simple idea, cascading up into a system of magnificent and terrifying complexity. So the next time you see a satellite image of a hurricane, that perfect white spiral against the deep blue of the ocean, you'll know what you're really looking at. You're not just seeing a storm. You're seeing the ghost of a straight line, a path forever bent by the spin of a world that is moving 1,000 miles an hour faster than you can feel. You're seeing the awesome, weather-bending power of a simple geometric fact. The invisible force bending our world. There is a story, often told, that a toilet in Australia spins the other way. It is a piece of familiar trivia, passed around quietly, that the water in a sink or a toilet drains in one direction in the northern hemisphere, and in the opposite direction in the southern hemisphere, all because the Earth is spinning. The simplest answer is that this is not true. It is a myth, but the myth itself points toward a much quieter, grander truth. There really is an invisible influence, a constant pressure on everything that moves across the surface of the Earth. It is a force so subtle you will never feel it. It is thousands of times weaker than gravity, and it has no measurable effect on the water draining from a sink. And yet, this same gentle, imperceptible push, when allowed to accumulate over vast scales, becomes powerful enough to shape the path of a 1,000-mile-wide hurricane. It steers the great currents of our oceans and helps form the weather patterns that define whole continents. It plays a silent, constant role in the world around you. This is the story of the Coriolis effect. It is the hidden architecture of motion on our planet. And today, we are going to explore not just what it is, but how it works, from the smallest, most intuitive scale, all the way up to the colossal storms that drift across our world. We are going to peel back a layer of our everyday experience and see the quiet mechanics of our spinning home. If this kind of calm exploration of the world helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near a coast, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. Let's begin with the myth. The idea is simple. In the northern hemisphere, water drains counterclockwise. In the southern hemisphere, it drains clockwise. For many years, this has been shared as a curious fact. It has even been used in demonstrations at tourist sites along the equator, where water is poured from a bucket to prove the effect on either side of an imaginary line. But this is a performance. The outcome is subtly influenced by the person pouring the water, or by the shape of the basin itself. The reality is that the forces at play in a sink are millions of times stronger than the Coriolis effect at that scale. The shape of the bowl, the angle of the water jets that fill it, even the tiny residual motion from the last time it was used. All of these things completely overwhelm any whisper of an influence from the Earth's rotation. It is like trying to hear a single, distant bird call in the middle of a thunderstorm. The sound is there, technically, but it is lost in the noise of everything else. So, for a moment, let's set the myth aside. To truly see the Coriolis effect in a basin of water, you would need a perfectly smooth, circular container, perhaps many feet across. You would have to let the water settle for days, or even weeks, in a room with no vibrations and no air currents, until it was perfectly still. Then, if you could release a plug from the bottom without creating any new motion, you might see a vortex form in the direction dictated by your hemisphere. But our homes are not designed for this kind of quiet observation. They are filled with chaotic, everyday forces. And so, the planet does not decide how a toilet flushes. This is where many explanations stop. But in setting aside the small story, we find ourselves at the edge of a much larger one. The question is not if this force exists, but where does it become strong enough to matter? If not in our sinks, then where? To find the answer, we need to leave the bathroom and imagine ourselves on a playground. Section 1. The analogy: making the invisible visible on a merry-go-round. One of the difficulties in understanding the Coriolis effect is that it is not a force in the usual sense. It is not a push or a pull, like gravity or magnetism. Physicists call it an apparent force, and the best way to understand what that means is to imagine yourself inside a rotating system. Picture yourself on a large merry-go-round with a friend. You are at the center, and your friend is on the outer edge. The ride is still. You toss a ball to your friend, and it travels in a perfectly straight line. This is our baseline. In a non-rotating world, an object in motion will stay in motion in a straight line. Now, the merry-go-round begins to turn. It spins counterclockwise, the same direction the Earth spins when viewed from above the North Pole. You are still at the center, and you throw the ball directly toward your friend. From your perspective, standing on the spinning platform, something unfamiliar happens. The ball seems to curve away to the right, missing your friend. It appears as though some unseen force has pushed it sideways. But let's imagine a third person is watching from the stationary ground outside the ride. From their outside perspective, the ball did travel in a perfectly straight line. The moment it left your hand, it was no longer physically connected to the merry-go-round, and it simply continued on its straight path. So why did it seem to curve? Because while the ball was moving straight, its target, your friend, was not. The platform rotated underneath the ball as it flew through the air. Your friend was moved out of the way. From your point of view on the ride, it is difficult to perceive the motion of the entire world you are standing on. All you see is the result. The ball did not end up where you aimed it. The only way for your mind to make sense of this is to invent a force. You observe that the ball curved to the right. That rightward curve, that apparent force that exists only for observers inside the rotating system, is the essence of the Coriolis effect. It is not a true force acting on the ball itself. It is a consequence of observing motion from a rotating frame of reference. The ball wants to go straight, but the ground beneath it is spinning. Let's try again. This time, you are on the outer edge, and you throw the ball toward the center. Again, it appears to curve to the right. This is because the ball, thrown from the fast-moving outer edge, carries with it a great deal of sideways momentum. As it travels toward the center, where the platform is moving much more slowly, it overtakes the ground beneath it. From your perspective, it veers to the right. This is the key. The force is an illusion created by rotation. And all of us are living on a giant, spinning merry-go-round. The grand reveal: scaling up to a planet. Our planet is a sphere, and it turns on its axis once every 24 hours. But not all parts of the Earth spin at the same speed. This detail is what allows our merry-go-round analogy to apply to the entire globe. Think of it this way. If you stand on the equator for a day, you travel the full circumference of the Earth, about 24,900 miles. To cover that distance in 24 hours, the ground you stand on, and the air above you, are all moving eastward at a remarkable speed of over 1,000 miles per hour, or about 1,670 kilometers per hour. You don't feel it, because everything in your immediate surroundings is moving along with you. It is like being on an airplane. You don't feel your speed because the aircraft is your constant frame of reference. Now, consider someone standing farther north, in a city like Anchorage, Alaska. They are much closer to the Earth's axis of rotation. The circle they trace over 24 hours is much smaller. To complete that smaller circle in the same amount of time, the ground in Anchorage is only moving eastward at about 500 miles per hour. And if you could stand directly at the North Pole, you would simply be spinning in place. Your eastward speed would be zero. So we have a planet where the ground moves eastward at over 1,000 miles per hour at the equator, and this speed steadily decreases as you move toward the poles. This difference in speed is the engine of the Coriolis effect on a global scale. Now, let's replace the ball from our merry-go-round with a parcel of air. Imagine a large mass of air near the equator. It is part of the atmosphere, and so it carries all of the equator's eastward momentum, moving at 1,000 miles per hour along with the planet. Now, imagine a low-pressure system forms farther north, perhaps over North America, and this equatorial air begins to move northward to fill it. As this parcel of air travels north, it holds onto its original eastward speed. But as it moves over places like Texas or Kansas, the ground beneath it is moving eastward much more slowly, perhaps at only 800 or 900 miles per hour. The air is now traveling eastward faster than the planet below it. So, to an observer on the ground, the air does not appear to move in a straight line to the north. It seems to drift off course to the east. Relative to its northward direction, a turn to the east is a turn to the right. There it is again, the same rightward deflection we saw on the merry-go-round, but now playing out on a planetary scale. The same thing happens in reverse. Imagine a cold blast of air from the Arctic, starting near the North Pole and heading south. That air has very little eastward momentum because it came from a place that was barely moving. As it travels south, it moves over land that is rotating eastward faster and faster. The ground is essentially rushing away from under it. From the perspective of the ground, the air appears to lag behind, drifting to the west. For something moving south, a deflection to the west is, again, a deflection to the asterisk right. No matter which way the air moves in the northern hemisphere, north from the equator or south from the pole, it appears to be deflected to the right. And in the southern hemisphere, it is a perfect mirror image. An air packet at the equator, moving at 1,000 miles per hour east, travels south toward Australia. The ground beneath it is moving slower. For an object moving south, this eastward drift results in a turn to the asterisk left. Likewise, a parcel of cold air moving north from the South Pole has little eastward speed. As the ground beneath it spins eastward faster, the air is left behind to the west. For an object moving north, a deflection to the west is, again, a turn to the asterisk left. And so, a quiet rule emerges for our spinning planet. Any object moving over a long distance will appear to be deflected to the right in the northern hemisphere, and to the left in the southern hemisphere. The effect is strongest near the poles and fades to nothing at the equator. This is why hurricanes cannot form on or cross the equator. The gentle, organizing spin they need to exist disappears. This is no longer a myth and a sink. This is a fundamental law of motion for our spinning world. We have seen the mechanism. Now, it is time to see the consequences. The payoff, the architecture of storms. This is where that subtle, imperceptible influence becomes visible on a magnificent scale. This is where it builds one of the most powerful and recognizable structures on Earth, the hurricane. At its core, a hurricane, also called a typhoon or cyclone, begins simply. It starts over warm ocean water, which heats the air above it, causing it to rise. As that warm, moist air ascends, it leaves an area of lower pressure near the ocean's surface. In response, surrounding air at higher pressure begins to move in to fill this area of low pressure. On a planet that did not rotate, the air would simply rush straight to the center from all directions. The storm would fill itself in and disappear. There would be no spin, no eye, no spiral structure. But our planet does spin. And every particle of air rushing toward that low-pressure center is subject to the Coriolis effect. Let's picture a developing hurricane in the Atlantic Ocean, in the northern hemisphere. Air from the north moves south toward the center. It is deflected to its right, to the west. Air from the south moves north toward the center. It is deflected to its right, to the east. Air from the east is deflected right, north, and air from the west is deflected right, south. A pattern emerges. No matter which direction the air comes from, it can never quite reach the center. Every time it tries to move in a straight line, it is gently nudged to the right. The result is that the air is forced to miss the center and begins to circle around it. This continuous rightward deflection traps the air in a spiral. It cannot get in, so it goes around. And from this, a counterclockwise rotation is born. That spiral is the defining architecture of a hurricane. The storm is not just a collection of wind, it is a highly organized, rotating system. Its structure is a direct physical manifestation of the Coriolis effect. A force too weak to stir a cup of coffee, when acting on 1 trillion tons of air over thousands of square miles, organizes chaos into a majestic and terrifying pinwheel. In the southern hemisphere, the exact opposite happens. Air rushing toward a low-pressure center is continuously deflected to the left. This forces the air into a *clockwise spiral. This is why a satellite image of a cyclone in the Indian Ocean is a perfect mirror image of a hurricane in the Atlantic. They are the same phenomenon, their spin a quiet reflection of which side of the equator they formed on. This same logic applies to the high and low pressure systems on any weather map. Each swirling pattern is a map of the Coriolis effect at work. It is the invisible choreographer of our atmosphere. Broader impacts, the global conductor. The influence of this invisible force does not stop with storms. It is so fundamental that its fingerprints are on nearly everything that moves across the globe. Just as winds are deflected, so are ocean currents. The major currents are organized into massive, continent-sized rotating systems called gyres. In the North Atlantic, as winds and density differences try to push water, the Coriolis effect deflects it to the right. This, along with the shape of the continents, guides the entire North Atlantic basin into a slow, colossal clockwise rotation. A part of this gyre is the Gulf Stream, which carries warm equatorial water up the coast of North America before veering right, heading east toward Europe. It is one of the reasons Northern Europe has a much milder climate than other places at a similar latitude. The same pattern holds in every major ocean basin. Gyres spin clockwise in the north and counterclockwise in the south. This same force dictates our global wind patterns. The trade winds, which blow reliably from east to west near the equator, are a product of this effect. Air flowing from high-pressure zones toward the low-pressure equator is deflected, to the right, westward, in the northern hemisphere, and to the left, also westward, in the southern hemisphere. These reliable winds became the highways for early global trade, their existence a quiet consequence of our planet's spin. The effect is so predictable that it must be accounted for in long-range ballistics. When a naval ship fires a shell over many miles, the Earth rotates a small but meaningful amount during the shell's flight time. To hit a target, the gunner must aim slightly to the side, correcting for the planet's movement. Even snipers making shots over a mile long must account for a deflection of several inches. It is a small correction, but in a world of precision, it matters. Perhaps the most elegant demonstration of the Earth's rotation is not a storm or a current, but a simple pendulum. In 1851, the physicist Léon Foucault hung a heavy pendulum from the dome of the Panthéon in Paris and set it swinging. A pendulum should swing back and forth in a fixed plane. But Foucault's did not. Over many hours, the plane of its swing appeared to slowly rotate clockwise. What was happening was that the pendulum was swinging in a fixed plane relative to the distant stars. But the floor of the Panthéon, the city of Paris, the entire Earth, was slowly rotating counterclockwise underneath it. Watching a Foucault pendulum is like sitting on the merry-go-round and watching the fixed background of the park appear to spin. It was the first direct, undeniable proof that the Earth rotates, its apparent motion another manifestation of the same quiet physics that steers a hurricane. So we return to where we began, the water in a sink. The story is a myth, a piece of scientific folklore. But it is a myth that points toward a deeper truth. The Coriolis effect is a story of scale. It is born from the simple fact that we live on a spinning sphere. At the human scale, in our homes, This force is an infinitesimal whisper, lost in the noise of 1,000 stronger forces. You will live an entire life without ever feeling its touch. But as the distances grow from feet to miles, and the times from seconds to days, that whisper becomes a voice. And over the scale of an ocean, that voice becomes an organizing principle. It is the architect of the atmosphere and the choreographer of the seas. That gentle, unceasing nudge, right in the north, left in the south, is what transforms a simple rush of air into the spiraling structure of a hurricane. It is a quiet reminder that we are passengers on a celestial body, moving at immense speeds, subject to laws that operate on a scale far beyond our immediate perception. The world has a hidden architecture, a set of rules that works silently beneath the surface of our experience. An invisible force is, at this very moment, bending our world. And now, you can see it too. If this quiet exploration into the planet's hidden mechanics helps you see the world a little differently, consider liking the video and subscribing to the channel. And wherever you are right now, feel free to share what the weather is like where you are, a small piece of the vast, rotating system we have been exploring today. Why your GPS is secretly lying to you. Long before our world was wrapped in a digital web of signals and satellites, the ground beneath our feet felt like a constant. The earth turned, seasons changed, and the stars wheeled overhead in predictable patterns. We built our understanding of the world on that stability. But in the quiet spaces between the data points, in the smallest errors of our most precise technologies, a different story is beginning to emerge. It's a story of a planet that is not quite as steady as we thought, and of the hidden ways our own lives are connected to its movements. This is a journey into one of those quiet connections. It begins with a familiar, modern experience, a map that seems just a little bit wrong. But it leads to a much deeper place, to the slow, massive shifting of water across continents, and to the subtle, almost imperceptible wobble of the Earth itself. If this kind of calm exploration into the hidden science of our world helps you find a moment of clarity, consider liking the video and subscribing to the channel. And wherever you may be watching from, feel free to share your location in the comments below. It's a fitting way to begin. It's a scenario that has become a quiet frustration of modern life. You are navigating an unfamiliar street, trusting a calm, synthetic voice to guide you. In 200 feet, turn right. You follow the instruction, only to find yourself at a dead end. You glance at your phone, and the small blue dot that represents you seems to float in a space between two streets, lagging just behind where you actually are. Or perhaps the feeling is more subtle. An estimated arrival time that adds minutes for no clear reason, even as traffic flows smoothly. A ride-sharing app that shows your driver circling a block away when they are, in fact, right outside. These are not catastrophic failures. They are small inconsistencies in the digital overlay we have placed upon the world, and they seem to be happening more often. They are small reminders that the map is not the territory. Our first thought is often to blame the most immediate thing. We assume a weak signal or a software bug in the application. We might even think of something cosmic, like a solar flare disrupting the satellites orbiting high above. And all of these things can, and do, cause errors. They are the usual sources of noise in a complex system. But they don't tell the whole story. They are the familiar explanations, and they mask a much deeper and more interesting problem. Before we explore that deeper truth, it's worth taking a moment to appreciate the system as it normally works. Understanding what usually goes wrong helps us see just how different and how significant the real problem is. The global positioning system is a modern marvel. A constellation of satellites orbits the Earth at an altitude of about 20,000 kilometers. Each one carries an incredibly precise atomic clock. They continuously broadcast a signal containing two pieces of information: the exact time the signal was sent, and the satellite's own location in space. Your phone listens for these signals. By measuring the tiny differences in their arrival time from at least 4 different satellites, it can calculate its position through a process called trilateration. It sounds simple, but the journey of that signal is a difficult one. As it travels from the vacuum of space into our atmosphere, it gets distorted. The ionosphere, a layer of charged particles far above us, can slow the signal down, much like a straw in a glass of water appears bent. Then, as it passes through the lower atmosphere, where our weather happens, changes in humidity and temperature can cause further delays. Scientists have developed models to correct for these effects, but they are not perfect. Down on the ground, the environment creates more challenges. In a city, surrounded by tall buildings, you are in what's known as an urban canyon. The weak GPS signal can be blocked, or it can bounce off several buildings before reaching your phone. This is called the multipath effect. Your receiver gets both the direct signal and a flurry of these reflected signals, which arrive a fraction of a second later. This confusion can shift your calculated position by hundreds of feet. For decades, the story of GPS inaccuracy ended there. It was a story of atmospheric physics and engineering limitations. But starting in the late 20th century, the scientists who dedicate their lives to measuring our planet, the geodesists, began to notice something else. They saw a new source of error, one that couldn't be explained by solar flares or skyscrapers. The very ground beneath our feet, the bedrock of the continents, was not as stable as we had assumed. The planet itself was moving in a way our models hadn't fully accounted for. And the cause was not something cosmic or geological in the traditional sense. The cause, it turned out, was us. The problem isn't just with your phone or with the satellites. The problem is with the Earth itself. We learn in school that our planet spins on an axis, an imaginary line that pierces the surface at the North and South poles. For nearly all of human history, we have treated these points as fixed. They are the foundation of our entire system of latitude and longitude, the grid upon which we build our maps and our navigation systems. But here is the quiet truth: the poles are not fixed. They are moving. The Earth wobbles. This is not a new theory. It is a measured, documented fact. For decades, the Earth's rotational pole has been drifting. But since the 1990s, that drift has accelerated, and its direction has changed. Between 1993 and 2010, the Earth's axis shifted by about 80 centimeters, or just over 2.5 feet. That may not sound like much on a planetary scale, but it is a colossal shift with quiet, profound implications. Imagine building a structure on a foundation that is slowly, but constantly, tilting. At first, the change would be imperceptible. But over time, stress would accumulate. The entire structure would become subtly unstable. Our global navigation infrastructure is that structure. And its foundation, the Earth's rotational axis, is tilting. This is not a natural, cyclical change that has been happening for millennia, though those cycles do exist. This is something new. This is a forced wobble, and we are the ones doing the forcing. The reason your GPS is becoming subtly less reliable is not a bug in the code. It's an unintended feature of the planetary system, one that we have inadvertently introduced. Our actions are having a direct, measurable impact on how our planet moves through space. And that simple, humbling fact changes our understanding of the world. To understand what's happening, we need to think of the Earth not as a perfect sphere, but as a slightly unbalanced, dynamic spinning object. If you spin a perfectly balanced top, it rotates smoothly. But if you add a small weight to one side, it will start to wobble. The same principle applies to our planet. Any change in the distribution of mass on or within the Earth can alter its rotation. For over a century, scientists have known that the Earth has a natural wobble. This phenomenon, called polar motion, consists of two main cycles. One is a 14-month wobble known as the Chandler wobble, which causes the pole to spiral by about 30 feet. This is the free, natural oscillation of our imperfectly shaped planet. The other is a smaller, annual wobble, caused by the seasonal movement of mass across the planet's surface, the shifting of atmospheric pressure and the locking up of water in winter snow and ice. For most of the 20th century, these two wobbles were the primary components of polar motion. They were predictable, cyclical, and well understood. But then, something changed. In the 1990s, scientists noticed the long-term polar drift had taken an abrupt turn. For most of the century, the pole had been drifting slowly toward Hudson Bay in Canada. But around 1995, it began moving eastward, and much faster. The cause was initially a mystery, but the prime suspect was climate change. As the planet warms, glaciers and ice sheets melt. That meltwater flows into the oceans, moving mass from the poles and spreading it out across the globe. This redistribution of weight changes the planet's balance, altering its wobble. And indeed, the melting of polar ice is a significant contributor. But when scientists modeled the effects of ice melt alone, the numbers didn't quite add up. There was a missing piece, another massive redistribution of weight they hadn't fully accounted for. The answer was hidden right beneath our feet. The single biggest driver of the Earth's recent polar drift is something we rarely think about on a planetary scale: groundwater. For agriculture, industry, and drinking water, humanity has been pumping water out of underground aquifers at a staggering rate. Between 1993 and 2010, humans extracted an estimated 2,150 gigatons of groundwater. It is a volume of water so vast it is difficult to comprehend. A significant portion of this water ultimately runs off into rivers and makes its way to the oceans. In effect, we are taking a huge amount of mass that was locked away inside the continents and moving it to the surface. A study published in the journal Geophysical Research Letters found that this redistribution of groundwater was the largest single factor influencing the drift of the rotational pole, even larger than the effect of melting ice sheets. The models showed that most of this effect was caused by water being pumped out of two main regions: Western North America and northwestern India. By taking mass from these mid-latitude regions, we have tilted the planet. It is a quiet, humbling realization. The act of irrigating fields in California and the Punjab is literally changing how the entire planet spins in space. So, the planet is wobbling, and its poles are drifting by a few inches each year. Why does this matter? The answer is that we have built a global civilization that depends on a level of precision that was unimaginable just a few generations ago. And that entire system is built on the assumption that the Earth is a stable platform. The wobble, small as it seems, creates a subtle but growing discrepancy between our digital model of the world and the world as it actually is. The global positioning system is based on a highly precise map of the world called the World Geodetic System 1984, or WGS-84. This isn't a traditional map, but a mathematical reference frame. It defines the center of the Earth's mass and a grid of coordinates fixed to the Earth's crust. The problem is, the system defines its orientation using the location of the poles as they were in 1984. When the true North Pole, the actual point where the spin axis intersects the surface, drifts away from the official WGS-84 North Pole, the entire coordinate system becomes misaligned with the planet's actual rotation. A drift of 80 centimeters in the pole's position means there is an 80 centimeter discrepancy between the reference frame our satellites are using and the real-world ground they are mapping. For everyday car navigation, this is an insignificant error. But for high-precision applications used in surveying, construction, and science, which aim for centimeter-level accuracy, it is a problem that must be solved. The agencies that manage our global navigation systems are acutely aware of this. They constantly monitor the Earth's rotation and issue corrections. Our GPS systems are continuously updated to account for the planet's wobble. So if we are correcting for it, what's the problem? The problem is the asterisk change. The old, predictable polar motion was easy to model. The new, accelerated, human-driven drift is less predictable. The faster the planet's orientation changes, the harder the race becomes to keep the map perfectly aligned with the territory. That little blue dot on your screen is lying to you, in part, because the very definition of location has become a moving target. This has consequences not just for location, but for time itself. The Earth's rotation has been gradually slowing for centuries due to the gravitational pull of the Moon. To keep our atomic clocks, UTC, in sync with the Earth's astronomical day, timekeepers have periodically added a leap second. But something new is happening. Deep within the planet, the churning of the Earth's liquid iron core is causing the planet's overall rotation to speed up. Since 2020, this acceleration has been strong enough to give us some of the shortest days ever recorded. This speeding up is so significant that we should have needed a *negative leap second, subtracting a second from our clocks, as early as 2026. The only reason we do not is because of climate change. A recent study in the journal Nature found that the slowing effect from melting polar ice is counteracting the speeding up effect from the core. The meltwater from Greenland and Antarctica has, by pure coincidence, delayed the need for this unprecedented timekeeping adjustment until at least 2029. Our global timekeeping system is now caught in a quiet tug-of-war between the mysterious dynamics of the Earth's core and the consequences of our fossil fuel emissions. Human activity has become a planetary scale variable, capable of postponing a global timekeeping crisis by accident. We are not just living on the Earth, we are actively, and often unknowingly, steering it. We began this journey with a familiar, 21st century annoyance: a glitching map on a phone. We looked at the usual explanations: bad signals, urban canyons, software bugs. But we found that the deeper story was something else entirely. The ghost in the machine is not faulty code. It is the shifting, wobbling, changing planet itself. We have moved so much water across the surface of the Earth that we have tilted its axis of rotation. It is a stunning display of unintended consequences, a reminder that we have become a geological force, powerful enough to nudge the spin of our own world. This isn't a story of impending doom. The Earth's wobble is subtle, but it is a story of a hidden vulnerability. We have wrapped our world in a delicate digital web of satellites and atomic clocks, a system utterly dependent on a stable planet. And we are discovering that the planet is not as stable as we thought, precisely because we are on it. The lie your GPS tells you is small, measured in centimeters and corrected for by diligent scientists working behind the scenes. But it is a quiet warning. It reveals a deep feedback loop. Our technology requires a stable Earth, but the act of powering that technological society is making the Earth less stable. The next time your map app seems a little lost, take a moment. Don't just blame your phone. Consider the immense, invisible chain of events that led to that glitch. Think of the water being drawn from a deep well, flowing across a field, and eventually into the sea. Think of the mass of a continent shifting, ever so slightly. And think of the planet itself, wobbling just a little bit more on its axis because of it. You are not just a user of the system. You are part of it. And the system is bigger, more complex, and more strangely interconnected than we ever imagined. Earth stops spinning. Sudden chaos versus a slow apocalypse. Right now, you are in motion. You, the world, and everything on it are part of a quiet, constant rotation, moving at over 1,600 kilometers per hour on an axis that no one can see. You do not feel it, and yet every part of our world, from the air to the oceans, depends on this silent, relentless movement. It is a fundamental agreement between our planet and the laws of physics. But what if that agreement were broken? What if, in a single moment, all of that motion simply ceased? Would the world end in a brief, violent scouring of its surface? Or would we witness a slower, stranger, and perhaps more unsettling transformation, as our planet gradually becomes something unrecognizable? This is a story of two possibilities. One is an apocalypse of sudden, overwhelming force. The other is a quiet, creeping metamorphosis of geography and time itself. To understand what would happen, we first have to understand the force at play, inertia. It is the same reason you feel a gentle pull forward when a car you are in slows to a stop. Your body holds the memory of its forward motion. Now, imagine that car is the planet itself, moving not at 60, but at over 1,600 kilometers per hour. And it is not just you. It is every building, every forest, the oceans, and the atmosphere. Everything has inertia. Everything wants to keep moving. So let's explore the layers of this thought experiment, beginning with the most immediate scenario. Sudden chaos. The moment the Earth stops, your inertia does not. If you were near the equator, where the rotational speed is at its highest, around 1,670 kilometers per hour, you and everything not anchored to the planet's deep bedrock would be carried eastward at a speed faster than sound. Gravity would still hold you, so you would not fly into space. Instead, you would become part of a profound redrawing of the planet's surface. Think of it less as being thrown, and more as the ground disappearing from beneath you at supersonic speed. The forces involved would be immense. Buildings, designed for the downward pull of gravity, would be met with a sideways force they were never meant to withstand. They would shear from their foundations, tumbling across the landscape and breaking apart into dust and debris. Forests would be laid flat. Cities would be erased in moments. Anything on the surface would be pulverized. But perhaps the most powerful force would be the air itself. The atmosphere, which normally spins along with us, would continue its journey eastward. This would create the most powerful winds in Earth's history, not just a storm, but a supersonic blast wave encircling the globe. The friction from this atmospheric shearing would generate enormous heat, likely igniting global firestorms. The sky would become an abrasive, superheated grinder, scouring the very crust of the planet. Even places far from the equator would not be spared. While the speed at the poles is nearly zero, a city at a high latitude would still feel winds far stronger than any recorded cyclone. There would be nowhere to hide on the surface. So, who survives this? Only those deep underground might be shielded. Scientists at the Amundsen-Scott South Pole Station, located on the very axis of rotation, would experience a moment of profound and bizarre stillness. For them, the world would just stop. The sun would freeze in its position, communications would go silent, and an unnerving quiet would fall as they became some of the last witnesses on a planet that had just torn itself apart. And if that were not enough, there are the oceans. The water of the seas, all 1.3 billion cubic kilometers of it, also holds colossal inertia. While the solid Earth has stopped, this immense body of liquid has not. The result would be a global tsunami, but not like one from an earthquake, which moves as a single wave. This would be the entire ocean, all at once, sloshing eastward. On every west-facing coast, a turbulent wall of water would rise. It would be a churning, chaotic mass, driven by winds already moving faster than sound. These mega tsunamis would surge inland for hundreds of kilometers, engulfing what the initial winds had not already cleared. The friction between the moving water and the stationary seabed would heat the oceans, and the churning would create a misty, indistinct boundary between sea and sky. The geology of the planet would also react. The sudden stop would create immense frictional stress in the Earth's crust, triggering planet-wide earthquakes on a scale we cannot measure. Tectonic plates would grind against each other, releasing millennia of stored energy in a single moment. The planet would ring like a bell, its surface a place where the lines between air, water, and Earth had dissolved. Civilization would be over. But for any survivors deep underground, the world would be just beginning to change into something new. A slow apocalypse. But what if the stop was not sudden? What if the Earth, over decades or centuries, just gradually slowed down? The initial, violent effects of inertia would be avoided. There would be no supersonic winds, no scouring of the surface. Instead, humanity would become a witness to a slow, creeping transformation of the very rules that govern our world. This is not an apocalypse of motion, but one of geography, time, and temperature. The first and most profound change would be to the shape of our world. The Earth is not a perfect sphere. Its rotation creates a centrifugal force that causes it to bulge at the equator. This bulge is about 21 kilometers high, and it pulls the oceans with it, creating a belt of deeper water around the planet's middle. As the Earth's rotation gradually slowed, this force would weaken. And without that force holding them, the oceans would begin to move. Gravity, now the dominant force, would pull the water toward the points where its pull is strongest, the poles. This would not happen overnight. It would be a process unfolding over generations. Coastal communities would notice the sea level beginning to drop, consistently, year after year. Someone living on the coast of Brazil or Indonesia would watch the ocean recede, exposing new land. Harbors would become useless. At the same time, in higher latitudes, the opposite would happen. The sea would begin a relentless rise. The lowlands of northern Europe and Siberia would slowly be swallowed by the expanding Arctic Ocean. Entire countries, like the Netherlands and Denmark, would disappear. In North America, the waters would creep up the Mississippi River Valley, while much of Canada would become a new, shallow sea. As the oceans migrated, the land around the equator would continue to emerge. Africa would merge with Europe. Asia and Australia would join. The Americas would become part of a single, colossal landmass. After centuries, once the rotation finally stopped, the world's geography would be unrecognizable. Two massive polar oceans would dominate the planet. And separating them would be a single, gargantuan supercontinent wrapped around the Earth's equator, a continuous ring of dry land. A person could, in theory, walk around the entire circumference of the planet. As the geography of our planet was being rewritten, so too would our concept of time. If the Earth stops spinning on its axis but continues its orbit around the Sun, a day would take on a new meaning. One full day-night cycle would last an entire year. For 6 solid months, one half of the planet would be locked facing the Sun, baked in relentless, unending daylight. Temperatures could soar well above the boiling point of water. Deserts would expand to consume vast portions of the equatorial landmass. Life would be scorched away. On the other side, the night side, the opposite would occur. With no sunlight for 6 months, the temperature would plummet to unimaginable lows. The atmosphere would cool, and gases like carbon dioxide could freeze and fall as a strange, dry snow. Photosynthesis would cease, causing a total collapse of the food chain. The internal clocks that govern sleep, mating, and migration in animals would be shattered. Most life as we know it would not be able to cope. The weather patterns we rely on would also break down. The Coriolis effect, a product of the Earth's spin, would vanish. Instead, a much simpler, more brutal weather system would emerge. Hot air would rise from the scorching day side and flow toward the frozen night side, creating monstrous, planet-spanning winds. But there might be one place where life could hold on. Between the burning day side and the frozen night side, there would exist a sliver of permanent twilight. A Terminator zone. Here, in this narrow band circling the globe, the sun would forever hang on the horizon. Temperatures could, in theory, be moderate enough for liquid water. It is in this twilight band that the remnants of life might find their last refuge. It would be a dangerous sanctuary. The immense temperature difference between the day and night hemispheres would drive ferocious, ceaseless winds along this zone. Perpetual, raging storms would be the norm. Human survivors would have to become a migratory species on a planetary scale, constantly moving to stay in the habitable zone, keeping the sun forever on the horizon. They would be living on the edge, a slow, nomadic procession around a dying world. And even there, a final, unseen vulnerability would be at work. The Earth's rotation is a crucial part of what generates its magnetic field. Deep in the planet's core, the spinning of molten iron creates a geodynamo, a shield that protects us from harmful radiation. If the rotation were to stop, the geodynamo would falter. The magnetic field would collapse. Without it, our planet would be defenseless. Charged particles from the solar wind would slam into our atmosphere. Cosmic rays would bombard the surface. Radiation levels would skyrocket. This constant bombardment would also begin to strip away our atmosphere over time, much as it is believed to have happened on Mars. Any survivors in the twilight zone would face a constant, invisible rain of deadly radiation. The sky might be filled with beautiful, eerie auroras, visible across the planet, but they would be a sign of our planet's final vulnerability. The reality. So, after this tour through two different kinds of planetary doom, the question remains: could this actually happen? The short answer is no. At least, not suddenly. The law of conservation of angular momentum is one of the most fundamental in physics. For the Earth to stop spinning, an equally colossal force would have to be applied in the opposite direction. The only thing we can imagine that could do that is a collision with another planet-sized object, and if that happened, the stop of our rotation would be the least of our worries. But the slow apocalypse, that is a different story. The Earth's rotation is slowing down. The process is known as tidal braking, and it has been happening for billions of years. The gravitational pull of the Moon creates tidal bulges in Earth's oceans. As the Earth rotates, it drags these bulges just ahead of the Moon. The Moon's gravity then pulls back on these bulges, creating a tiny but constant frictional drag on the Earth's spin. It is like a gentle, planetary scale brake. The effect is incredibly small. Atomic clocks have shown that the length of a day is increasing by about 1.7 milliseconds per century. A few 100 million years ago, a day on Earth was only about 21 hours long. While there are sometimes temporary, short-term accelerations in our planet's spin, the long, slow trend of deceleration continues. So, while the slow apocalypse is a physically plausible future, it is a journey that will take billions of years, likely longer than the Sun itself has left before it becomes a red giant. It is not our future. The spinning of our world is the silent engine of our existence. It sets the rhythm of day and night, shapes our weather, holds our oceans in place, and generates the shield that protects us from the cosmos. It is a force so constant we are almost entirely oblivious to it. Imagining a world without it, whether through the chaos of a sudden stop or the slow transformation into an alien planet, is a powerful thought experiment. It forces us to see the delicate, intricate balance of forces that make life here possible. The ground beneath our feet feels solid, but it is part of a grand cosmic dance. And thankfully for us, that spin is one of the most reliable things in the universe. The next time you feel the wind, or watch the tide, or see the sun rise, it is worth remembering the silent, planetary motion that makes it all possible. The spin is life. And for the foreseeable future, the Earth will keep spinning on. Your body follows a clock you can't see. Right now, you are part of a silent, constant motion. Your planet is turning on its axis, carrying you through space on a journey that never pauses. This movement is imperceptible. The air in your room is still, the ground beneath you is steady. And yet, this silent rotation is one of the most powerful forces in your life. It is the quiet conductor of your every waking and sleeping moment. Perhaps you have woken up just moments before your alarm, as if some internal system knew the time. Or maybe you have felt that wave of exhaustion in the middle of the afternoon, a crash that seems to come from nowhere. These are not random occurrences. They are the whispers of an ancient timepiece, a biological clock hardwired into your DNA. For billions of years, Life on this planet has been tethered to a single, unyielding rhythm, the 24-hour spin of the Earth. That planetary rotation created the cycle of day and night, and in doing so, it etched its schedule deep into the fabric of biology. This is not just about sleep. This clock dictates your energy, mood, hunger, and strength. It is a hidden layer of reality, a rhythm you cannot see, but one you cannot escape. This is a journey into that clock, an exploration of how our planet's spin became the secret rhythm of your life, governing everything from your sleep-wake cycle down to the silent dance of molecules inside your cells. The planetary pacemaker. To understand the clock inside of you, we must first look outward, to the colossal clock that created it, the Earth itself. Our planet is a remarkably consistent timekeeper. It completes one full rotation on its axis relative to the distant stars once every 23 hours and 56 minutes. Because of Earth's simultaneous orbit around the Sun, the time from one sunrise to the next, the solar day we live by, is slightly longer, averaging 24 hours. At the equator, the planet's surface moves at over 1,600 kilometers per hour. The reason you are not flung into space is because everything, the ground, the atmosphere, and you, is moving along with it. It is like being on an airplane traveling at a constant speed. You can walk through the aisle and your drink does not fly to the back of the cabin, because everything inside is moving at the same velocity. We are all passengers on a spinning planet. The most fundamental consequence of this spin is the cycle of day and night. As the Earth rotates, one half faces our star, the Sun, and is bathed in light. The other half faces away, into the darkness of space. This is the most profound and predictable environmental change on our planet, and it has been this way for more than 4.5 billion years. Life did not just emerge on this spinning planet, it emerged because of its spin. The predictable rhythm of light and dark became the primary organizing principle for almost all living things. The earliest single-celled organisms, like cyanobacteria, developed light-sensitive proteins billions of years ago. These proteins allowed them to anticipate daytime, to perform photosynthesis, and nighttime, a time to rest and repair. They had a rudimentary clock. This evolutionary pressure continued for eons. Plants developed behaviors tied to this cycle. Animals evolved to find a niche within the 24-hour window. Some, known as diurnal creatures like us, are active during the day. Others, the nocturnal ones, seized the opportunity of darkness. Every one of these strategies is a solution to the same problem: how to best survive on a planet that offers a predictable rhythm of light and energy, followed by darkness and recovery. This planetary cycle is the metronome that all of life has learned to dance to. It forced biology to develop a way to not just react to the sunrise, but to anticipate it. And to follow that schedule, life had to build a clock. The master clock in your brain. The journey from the planet's spin to your own internal rhythm is one of the more elegant stories in biology. The central mystery for a long time was how our bodies, complex systems of trillions of cells, manage to stay synchronized with this external planetary rhythm. The answer lies in a tiny region deep within your brain. This is the location of your master clock. Scientifically, it is called the suprachiasmatic nucleus, or SCN. The name simply describes its location. Supra means above, and chiasmatic refers to the optic chiasm, where the optic nerves from your eyes cross. So, the SCN is a small cluster of neurons sitting right above the point where information from your eyes enters the brain. This location is not an accident, it is the key to its function. The SCN is made of only about 20,000 neurons, a minuscule fraction of the 86 billion neurons in the average human brain. Yet, this tiny nucleus acts as the master pacemaker for your entire body. But how does it know what time it is outside? It does so through the most direct route possible: light. When light enters your eyes, a A portion of that signal is captured by a special set of cells in your retina. These are not the rods and cones used for forming images. They are called intrinsically photosensitive retinal ganglion cells, IPRGCs, and their job is to detect the presence of ambient light, particularly blue light. These cells contain a photopigment called melanopsin, which is highly sensitive to the blue light abundant in natural daylight. The signal travels from these cells directly to the SCN. This is the daily reset signal. Every morning, light exposure synchronizes your internal clock with the external 24-hour solar day. This is why morning light is so crucial for feeling awake and maintaining a healthy sleep schedule. It is the anchor for the entire system. What is truly fascinating is that the SCN is an autonomous clock. Scientists have discovered that if you take SCN cells and keep them alive in a petri dish, isolated from all external cues, they continue to fire rhythmically in a cycle that is approximately, but not exactly, 24 hours long. In humans, this free-running internal clock averages around 24.2 hours. This slight drift is why we need the daily signal of light to reset our internal clock and keep it perfectly aligned with the Earth's 24-hour rotation. Without it, our sleep-wake cycle begins to drift later each day. The discovery of the SCN revealed a tangible mechanism connecting the astronomical cycle of our planet to our own neurobiology. It showed that a part of our brain is, in essence, constantly observing the sky. But the SCN is only the conductor. It does not play the instruments itself. For that, it must communicate with the rest of the body, with an entire orchestra of smaller clocks. The body's orchestra of clocks. The suprachiasmatic nucleus may be the conductor, but it is not a soloist. To understand how this internal clock governs your body, you have to imagine an immense orchestra. The SCN stands at the podium, setting the tempo. But every section of the orchestra has its own internal sense of rhythm. These are the peripheral clocks. Practically every organ in your body, from your liver and heart to your muscles and skin, contains its own biological clock. These clocks are genetic, operating within individual cells. They are composed of clock genes that turn each other on and off in a continuous feedback loop that takes about 24 hours to complete. This molecular ticking is happening inside you right now, in trillions of cells simultaneously. If left to their own devices, however, these peripheral clocks would fall out of sync. This is where the SCN's role as conductor becomes critical. The SCN synchronizes this bodily orchestra using the nervous system and hormones. Two of the most important of these are cortisol and melatonin. Cortisol's natural daily rhythm is essential for alertness and energy. In a properly aligned rhythm, the SCN signals for cortisol production to begin ramping up in the early morning, before you wake up. This is what helps pull you out of sleep. Cortisol levels peak in the morning and then decline throughout the day. On the opposite side of the cycle is melatonin, which acts as a signal that nighttime is approaching. As daylight fades, the SCN detects the diminishing light and signals the pineal gland to begin producing melatonin. Melatonin does not induce sleep like a pill. Rather, it informs every cell in your body that it is time to prepare for rest and repair. Through this elegant push and pull, the SCN coordinates all the peripheral clocks. Your digestive system, for instance, has a clock that is primed to be most active during the day, anticipating mealtimes. When you eat late at night, you force the digestive system to work when its clock says it should be resting. Your physical strength also follows this rhythm, with most people experiencing peak muscle performance in the late afternoon. Even your immune system is timed. The immune response is generally heightened at night, which may be why symptoms of illness can feel worse after the sun goes down. Every aspect of your physiology, blood pressure, body temperature, mental alertness, is scheduled. It is an intricate system, a symphony of trillions of cellular clocks all kept in harmony by a tiny conductor in the brain, which takes its cues from a spinning planet. For millennia, this system worked flawlessly. But our modern world has introduced an element that can throw the entire orchestra into disarray. When the rhythm breaks. For most of human history, our internal clocks and the external environmental clock were in synchrony. We rose with the sun, worked by its light, and when it set, our world became dark. In little more than a century, we have radically altered this relationship. We have invented a world of artificial light, global travel, and 24/7 schedules. When our lifestyle fights against our internal rhythm, the clock can break. This state is known as circadian misalignment, and it comes with consequences. The most acute example is jet lag. When you fly across time zones, your body is in a new light-dark cycle, but your internal SCN is still running on the time of your departure city. It expects light when it is dark outside and darkness when the sun is high. The SCN tries to adjust, but it can only shift by about an hour each day. The result is fatigue, brain fog, and digestive problems. You feel unwell because, on a biological level, your body is in a state of chaos. While jet lag is temporary, millions of people experience a chronic version of it. This is the reality for shift workers. Forcing the body to be awake and working during the night is a profound biological stressor. Over time, this chronic circadian disruption is linked to an increased risk for obesity, type 2 diabetes, heart disease, and certain cancers. The World Health Organization's International Agency for Research on Cancer has even classified night shift work as a probable carcinogen for this reason. But you do not have to work the night shift to experience circadian disruption. Many of us live with a more subtle form called social jet lag. This is the mismatch between our body's clock and our socially imposed schedules, especially the difference between our sleep patterns on workdays versus free days. If you wake at 6 a.m. during the week but sleep in until 10 a.m. on the weekend, you are giving your body a 4-hour dose of jet lag every weekend. The biggest culprit driving this is artificial light, specifically the blue light from our screens. Remember those special cells in our retinas? They are most sensitive to blue light. To our ancient brains, blue-rich light means one thing: midday sun. When you stare at your phone or computer late at night, you are sending a signal to your master clock that says, it's still daytime. Do not release melatonin. This exposure to light at night pushes our entire rhythm later. Then, the alarm clock forces us to wake up before our body is ready. We have created an environment that directly conflicts with the biological programming refined over millions of years. We are trying to live a 24/7 lifestyle with a body that is fundamentally designed to live by the rhythm of the sun. The unseen hand of the spin. The influence of Earth's 24-hour rotation on our biology is profound. But the effects of this silent spin do not stop with our sleep schedules. The rotation has other, equally powerful consequences that shape the world we experience. One of the most dramatic of these is the Coriolis effect. Because the Earth is a rotating sphere, any object moving over long distances across its surface is deflected from a straight path. In the northern hemisphere, this deflection is to the right. In the southern hemisphere, it's to the left. Let's address a popular myth. The Coriolis effect does not determine the direction water spins down a drain. The forces are too weak over such a small area. The shape of the basin has a much greater influence. On a large scale, however, the Coriolis effect is a dominant force. It is the architect of our planet's weather patterns. Air flowing from high-pressure to low-pressure systems is deflected, creating massive, rotating weather systems. This is why hurricanes in the northern hemisphere spin counterclockwise, and cyclones in the southern hemisphere spin clockwise. The air rushing towards the low-pressure eye is deflected by the spin, initiating the storm's rotation. The effect is zero at the equator, which is why hurricanes cannot form there. The power of this force is not just theoretical. During World War I, German gunners firing a long-range cannon at Paris found their shells were landing consistently almost a mile off target. They had to consult physicists, who instructed them to account for the Earth's rotation in their calculations. The planet was moving out from under their artillery shells. Earth's spin also dictates our global system of time. The same rotation that gives us day and night is the basis for our 24 time zones. Our entire globalized society runs on a schedule dictated by Earth's rotation. From the rhythm of your sleep to the direction of a storm, the evidence is all around us. We live on a stage that is constantly and silently spinning. We began by considering ourselves as passengers on a spinning planet. We have seen how that spin creates the rhythm of day and night, a rhythm so powerful that life learned to internalize it, to build a clock from its own genes. We journeyed into the brain to find the master conductor, the suprachiasmatic nucleus, which uses light to synchronize an orchestra of clocks throughout our body. We have also seen the consequences of defying this ancient rhythm. The story of your body clock is the story of your connection to the planet. Understanding this connection is not just a fascinating piece of science, it is a key to living a healthier life. The good news is that you can begin to realign your rhythm with a few simple principles. First, an alignment with morning light is essential. As soon as you can after waking, exposing your eyes to natural daylight for 10 to 15 minutes provides the most powerful signal to anchor your clock for the day. Second, consider minimizing light at night. In the hours before bed, dimming the lights in your home and avoiding bright screens allows your body's natural production of melatonin to rise, preparing you for sleep. Third, there is value in consistency. Trying to go to bed and wake up at roughly the same time each day, even on weekends, can prevent the shock of social jet lag and keep your body's clocks in harmony. And finally, consider the timing of your meals. Eating within a consistent window during the daytime and avoiding large meals late at night allows your metabolic clocks to function when they are most efficient. If this quiet exploration into the hidden rhythms of life has been helpful, consider subscribing for more stories about the science that runs our world. The world can feel unpredictable, but beneath it all is a rhythm of profound consistency. It is in the turning of the earth and in the ticking of your cells. Every sunrise offers a new beginning. Every sunset is a quiet invitation to rest. The next time you feel that pull towards sleep, or watch the sun dip below the horizon, take a moment. That feeling is a quiet reminder that our biology is not separate from our planet, but an ancient and elegant expression of it.